So we're down to it. We're going to talk about these things called iterated or double or repeated integrals. We've already introed it in 14.1. I gave you the basis of what this means, how we create these things. Now this section is about how we do them without adding up a whole bunch of rectangles and taking a limit, because that's really annoying. So just like in Calc 1, we start that idea, we get an integral, and we just practice antiderivatives. Now in Calc 3, we practice we did the setup, and now we're just going to practice doing these double integrals. I'll show you exactly how to do it. I'll hopefully show you the most important pieces, because when I was taking Calc 3, my teacher never told us what to do with this, and that is the most important part. I floundered all through Calc 3 because this, what R does, how to set up R, how to make your double integral from R, is the hardest part. If you know how to do integrals. And do you know how to do integrals? Then that's going to be pretty darn hard if you don't. If you do know how to do integrals, there's no new integration techniques. There's nothing new. You know how to do integrals. The setup is the most important part. How to go from given a random R to an actual setup of a double integral, that's the most important piece I can tell you. Once you set up the R correctly, once you set up your double integrals correctly, the rest of it follows fine. But the setup is the most important. That's what we're going to focus on, is your ability to go from a defined region to a double integral. Does that make sense to you? That's the whole goal of today. I'm not going to spend a whole lot of time showing you integration technique. I'm basically going to focus on setup, do the integrals as fast as possible, and then get to an answer. Your job is to learn the setup and practice the integrals later. Is that clear? That's my goal for today. So how do we get there? Well, the first thing is to recognize what we did in the last section. For any function of two independent variables, the volume under that surface, verify that's a surface, the volume under that surface, but over a specific region R, is given by this. That's what a double integral means. It's giving us the volume under a surface. Just like a single integral was area, we're now extending the dimension. So we're extending the dimension here as well. Like one dimension higher than area is volume. One integral higher than a single integral, a double integral, gives us volume. That's our plan. So I do want to come back to this though. What the dA stands for. Back in 14.1 last section, when we went through this, we added up a whole bunch of areas of rectangles. Do you recall doing that? We went to the first X column and added up all the rectangles, and the next one add up all the rectangles along Y. And I stated something about something called Fubini's theorem. And I said, does it matter how we find area? Delta X times delta Y or delta Y times delta X? Does it matter?
No.
Well, that delta X times delta Y, that gave us the area for each of those rectangles. And since that multiplication, the way we find those areas is commutative, here's what this says. The volume over a region of a function with two independent variables, basically the volume under the surface, given by the area of each rectangle. So here it is. Rectangle along the X, subinterval along the X, subinterval along the Y, multiply them, you get the area of each rectangle. All the rectangles have the same area. Does that make sense? When we did our whole limit, you have to watch 14.1 again, but when we did all that stuff, all the deltas basically turned to d's. So the delta A became the dA. Here's what I want you to glean from this. That infinitesimal area that we get for each rectangle, this equals dx dy. Just like delta x delta y equals delta A, dA equals dx dy. But wait. If delta A also equals delta y delta x, then what else could dA equal?
dy.
Yeah. Here's the thing about it. That means that listen carefully, for rectangular regions, that's how we started this whole thing in 14.1. Well, I want you to firstly notice how rectangular regions are going to look for you. So we're going to get to an example very shortly, but how this is going to look, it's going to give you an integral, double integral over R of some function. It's going to be defined, dA, that's fine, but that R has to be defined somewhere. And so the definition of R is going to be off to the side somewhere. We're going to look at that first. Here's how rectangular regions are going to look for you. They're going to say, hey, you got a series of points, all right, x ordered pairs, which we plug into our function. Here's how rectangular regions are going to be written. For rectangular regions, think about this. X's and Y's are on a plane, correct? This region is going to be on a plane. The double integral says over that region on the plane is some surface. Take the region, let's imagine it's a rectangle, shoot it up there, and then find the volume of that almost rectangular prism you get. Just the top's not a rectangular prism. It's a surface now. That's the whole reason why we have this calculus, okay? That's the idea here. Well, if I have a rectangular region on my xy plane, then it has to be bound by constants. It's got to go from x, one number to another number, and y, one number to another number. I don't have any lines that aren't constant on that. So for rectangular regions, they're going to be really easy to see how they're defined. I'm going to have a series of points such that x is bound by two numbers. Verify this. If x equals a, I get a line just at the x, so if x equals a, vertical line. Make sense? If x equals b, vertical line. That's what that means. Well, but wait. That's an infinite region forever. I also need to define y. If y equals c, horizontal line. If y equals d, horizontal line. This right here is the rectangular region on the xy plane that I'm finding the volume over. So this thing shoots up, it intersects the surface, and I'm finding the volume of that rectangle being shot into space, connecting with our surface. Show of hands if you're okay with that one. So this right here tells you rectangular region. It says x is bound by constants, y is bound by constants. That's always going to give you a rectangle on the xy plane. Have I made that make sense to you? Rectangular regions should be really, really easy to see. They're just numbers here and here, numbers here and here for both x and y. Make sense? But wait. Because of this relationship, that means that there's actually two ways to set up any double integral. Look at it, look at it. If these things are commutative, I can switch this around. That means that for every double integral, I could have dx dy, or I could have dy dx. Well, so for every single one of these, by the way, before we go any further, I want to just, some people get this all jacked up. I know I did when I was a student. Is this the thing that's giving you this region? No. This definition gives you the region. This thing is hidden. This thing is the surface. Hopefully, it needs to be a continuous surface. This thing is the surface over that region. Does it make sense? You never draw this, ever. It's going to be in 3D. What we do draw pretty much every time, unless they're rectangular, I'll show you why, we do draw is the region. That's what we draw. The thing on the XY plane. That's really convenient because you're used to graphing lines and curves and rectangles. That's fine. We don't graph this, we do graph that. So anyway, we now have this choice to make. Because of the nature of how we created this stuff, because of the nature we can commute these two things, then the dA can be either dx dy or dy dx. Do you guys understand the concept that this is one or the other of those? Show of hands if you do. You get that. Okay, that's fantastic. We gotta show it's one of these two things. Here's the most important thing I can tell you in how to set up rectangular regions or pretty much any double integral ever. You must, absolutely must, make sure that whatever variable comes first is connected with the bounds of that variable here. So if my dx is first, what should be on this inside integral? X values or y values? They have to be x values. Okay, what are the two x values? How do integrals work? Do they start from the smallest one or start from the biggest one? Which would be, you can tell it's A, right there, it's smaller. You with me? The way integrals work is very much like order operations. Inside first, then outside. So when we're matching this up, hey, if you got a dx, you better make sure that these are x values right there. If they're not x values, they got to be x functions, something x equal to. If this is a y, your outside integral, so outside dy, outside integral, that also has to match up. So x's match with x's, y's have to match with y's. Tell me the two y values, please. And they go in that order. So let's see if you're paying attention, right side people. This is now dy dx. What has to go on the first inside integral to match up with the dy? What goes here and here? And here? That's probably the biggest key. You must absolutely match up the correct numbers with the correct variable. So if x is between a and b, if I'm doing dx, this first integral matched with the dx has to be a and b. If y is between c and d, the outside think order operations, that's what I mean, first and then second. First and then second. X's with x's, y's with y's. Y's with y's, x's with x's. Show of hands, feel okay with the setup on that one. It's going to be easier once we get our example, but I need you to understand the nature of this thing. If I flip these around, I flip these around too. That's a big deal. Do you guys get it? I'm not just randomly put numbers up there. I thought that when I was in Calc 3. It was like, just put numbers up there and do it, man. Well, now, here's the whole point. If there's two different choices, which one's right? Does it matter? They're both equal. So which one's right? The one that's easiest. The one that's, and I'm not joking, because sometimes the way we set these up can make our problem much easier, and that should be read possible. Sometimes they're impossible or extremely hard. So here's what I have to say. Whole recap. Double integrals, volume. That's all you got to know. Volume under a surface over a defined region. Can't be an infinite region for us right now. Over a defined region. Does that make sense? How we set that up for rectangular regions doesn't matter. You can do x's first or y's first, but you got to match up the x bounds with the dx. That integral's got to match. You got to match up the y bounds with the dy in whatever order you choose. That's the biggest idea. Have I explained it well enough for you? Yes or no? Yes. Everybody, yeah? No? Sure? Okay. So, which one's right? They're both right. They're equal. So I'm going to say, or means they're equal. That, by the way, is called Fubini's theorem for rectangular regions. I'm not going to write it. I'm just verbalizing it. I basically talked about that in 4.1 and showed you right where it could be proved. I said, hey, Fubini's theorem, blah, 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 blah. This is what Fubini's theorem says. It says that these two things are equal. You guys ready for an example? Yes. Let's do it, man. I'm excited. It'll be fun. So all the legwork's done. We did that in 14.1. You now have hopefully a really good understanding of setting these things up. Let's practice. So let's do a double integral. Go ahead, have a seat. Double integral over that. What's this thing giving us? Is this giving us the region, or is this giving us a surface? Surface. Okay. Let me ask you a question. Can we do that integral right now? Right now. Can we do that double integral right now? Yeah. If I just keep on looking at you, are you going to change your answer back and forth? Yeah. No. I don't know. Oh no. What do I know? You know lots. You know lots. But one thing you might not know, what we've been talking about, is in order to tell me the volume under a surface, you need to tell me what it's over. Have I told you what the region is yet? No. You have to have a region, or you can't do this. So I got to give you two things. I got to give you double integral. I have to give you a surface, a function somewhere, and I have to give you a region. So here's the region. For me, listen, in most textbooks, some of the times they just give you double integrals, it's already set up and you just do it. That is not my style. The most important thing I can teach you is how to set up a double integral. Do not expect on your tests that any double integral will be set up for you already. I will always give you something like this, where you're given a function, you're given a region, you gotta know how to take that region and make your double integrals from it. It's not super hard, and that's my job, is to tell you how to do it. I'm gonna do a really good job of telling you how to do it, but you gotta be really good at it. Okay, by the end of today, end of your practice, we gotta be able to take that region and adequately set up a double integral. You with me? So here's our region. Our region says, I want our points to be according to this. Left-siders, this is our region, true or false? Right-siders, this is our region, true or false? What type of region is that? How can you tell immediately it's a rectangle? How can you tell? Can you tell? If you were to draw it, we'd have basically this, I think I had it right here, this picture right here. We'd have X is good, well, let me restart that. It's like tic-tac-toe right now. Where's X going from?
-1, 0.
Let's try the X one.
1, 0, 0.
X goes from 0, this one, to 1. What's Y going from?
-1, 0.
This is the picture of our region. Could you draw that every time? For rectangular ones, we typically don't because they're really easy to set up. You're just going between some numbers. And Fubini's theorem says it doesn't matter which way you go. So we're just going between some numbers here. For things that aren't rectangular, you better believe we're going to be drawing a lot of those things, okay? Especially some of the more difficult ones. I'll show you how to do that. But for right now, the main things I can get you to know here is that's a surface. The region right now is rectangular because I'm going constant to constant, constant to constant. Constants are vertical lines or horizontal, verify that. Where they intersect is going to create a rectangle. What we're doing here is taking the surface over that rectangle and finding the volume. That's the idea. Show of hands if you're okay with that one. Now how? Well, this says, I don't care how you set them up. As long as you choose dx with x's or dy's with y's first. The rest of it just follows. Let's go ahead and try it. I will give you some pointers. The order doesn't really matter, but if one way's easier than the other, choose it. For instance, I see that x goes to from 0 to 1, so that means I'm going to be plugging at 0 at some point. Does that make sense? I want to do that first. I want to plug in 0 first to make my evaluation easier. So I'm going to choose to go dx first with 0 to 1, and then dy from -1 to 2. Make sense? So let's try to set that up. So how we change from this format to an actual double integral we can do is by looking at our region and set up appropriately. So let's start this. Is this going to change right now? No, we don't draw that. That is our surface over the region we just described. The dA has to change. The dA, you never leave a dA. You're either going to put dx dy or dy dx. In this case, I want to go from 0 to 1 first. If I want to go from 0 to 1, ladies and gentlemen, what type of values are those values? Are those x values or y values?
X values.
Listen, this is not in any textbook. This is poor. Some people would argue this is poor notation. I don't care. It helps a tremendous amount. If those are x values, you have my permission to put x equals 0 and x equals 1. You know why? Because if you put those, always match that variable to the first thing. X equals dx, x equals dx. Match that up, it'll save you a lot of headaches. Does that make sense? So we want to match that up. Make sure our x bounds match up with our dx. Should finish you're okay with that one. Okay, well, now we do got to finish this thing off. What's the next thing I would write? Well, that means that our outside integral, so inside integral must match. X's with x's, outside integral must match. Y with y's. Everyone in class right now, tell me what number should go right here. What type of a number is that, an X number or a Y number? And ends at?
2.
You're not going to see Y equals and X equals in any book. That's something I do because it helps me out a ton. I like to check my work this way. These are X's, matches up with X's. These are Y's, matches up with Y's. Do you like that too? Do you guys see how that matches? It's a great way to check your work. You don't have to put it, but that helps me. For real, head nod if you're okay with it.
Yep.
Could you have done it differently by switching these things around?
Yeah.
Why don't you do both? Now, let's go ahead and let's do the integral. The way integrals work is we focus on the first inside integral, do that one, with respect to whatever variable's listed. So, hey, y'all remember partial derivatives? Remember partial derivatives, how it was with respect to one variable and the other one's held constant? If integrals are antiderivatives, then double integrals are anti-partial derivatives. We're just going backwards. So let's look at this inside basically order operations. Just look here, and you tell me what variable I'm integrating with respect to. Perfect. Let's go ahead and let's do that. I'm going to keep my first integral. This is going to be hanging on for a little while. You do have to write it every time. But my inside integral, when I'm doing that, hey, everyone in class right now, what's the integral of x with respect to x, please? Oh, good, you still remember. What's the integral of y squared with respect to x? Wait. Does it go to 0? Derivatives, constants go to 0. Integrals, you never go to 0 with integrals. You at least get an x. So just like we did in partial derivatives, you treat it like a constant. You're going to treat whatever is not that variable as a constant. I like to use 7. If this was plus 7, I'd get plus 7x. If this is y squared, I'm going to get plus y squared x, or xy squared, either way you want to do it. By the way, could you check your work? How would you check your work? Take a partial derivative with respect to whatever variable you just integrated with respect to. Should fans feel okay with that one? Now, here's the cool thing about double integrals. Double integrals are really that. 2 times you're doing integrals. Which means if we can set this up correctly and integrate with respect to x, now we get to evaluate before doing the next integral. Half our stuff's going to be gone. In fact, here's what has to happen. Please listen carefully. This blows by a lot of people the first time they ever see this, okay? Here's what has to happen. Whatever variable you just integrated with respect to must disappear. Here's why. If your x's don't all disappear, you ain't going to be able to integrate with respect to y. Does that make sense? All of this variable we're going to plug in for, correct? All of this variable, that's why we write this. You're going to plug in for x, these numbers. X is going to be gone. Make sense? You need to be left with only whatever variable that is. If that doesn't happen, you've made a mistake. Should fans feel okay with that one? You sure? So, okay. Well, now let's evaluate it. What are we going to be plugging in? 0 and 1 for what? Write that down. So this, over on the right-hand side, you've seen this before. We're going to be plugging in x equals 0. We're going to be plugging in x equals 1. Ladies and gentlemen, my best piece of advice to you is this. Write down everything I just wrote down. Do it exactly this way. When you're plugging in a number, you make sure that you put what variable you're plugging in for, because you can tell, right? People are going to get going really fast on their test. You can see what they're going to do. Some people are going to be plugging this in for y, just because they do, even though it's not appropriate. Write down whatever variable you're evaluating, put the number, and then evaluate it. By the way, I'm missing one thing. What am I missing right now? dy. So let's continue. When I evaluate this, am I still going to have this first integral?
Yes.
If you want to drop the whole y, that's okay. That's completely optional. It's just something I do. It helps me. Let's plug in. Which one do you plug in first, the 1 or the 0? Everyone in class right now, what do you plug the 1 in for, the x or the y?
Yes.
So we get 1/2. Sorry, just 1/2. Plug in 1, you get 1/2 plus what? Plus what?
Y squared.
Perfect. So we plugged in x equals 1, that gives us 1/2, x equals 1, that gives us y squared, minus what?
Zero.
Why?
So you plug in 0, everything goes to 0.
Perfect, love it. dy. Let's clean that up a little bit. I don't need the 0. I want you to notice a couple things. Here's a 20-second recap to make sure we're all on the same page. You follow? Rectangular regions go between constants. There should be no functions up there, just constants. Rectangular regions can interchange. As long as you match up the x's with the dx on the inside, y's with the dy on the outside, or vice versa. That's absolutely fine. Do whatever way is easiest. That's cool. Now, the most important thing I can show you besides the setup is, as you're doing the integral, whatever variable this is must completely disappear before you do your second integral. It's got to be completely gone. And you can see that it does. As soon as we evaluate for x equals numbers, x's are all gone. And then we get something that looks like Calc 1. That's the whole nature of this. How we change Calc 3 into Calc 1. So we change a double integral. Now it's just a basic integral. It should look very, very doable for you. Should have this variable with respect to that variable, same variable there. Does that make sense? Can you finish that off? Go for it. I'll do it on the board. But honestly, we're not really focused on doing basic integrals. We're focused on the setup here. So let's go as quick as possible to get it done. And hopefully you're noticing as we're going through it, the reason why we have to match up y's here and x's here is because if we have these things reversed, these have to be y values. If you end an integral and you have x's in here, you have y's here, there's nothing to plug in for. You'd get stuck. It doesn't work. You can go ahead and double check your work, but I believe I got 9/2 when I did that one. Anybody else get 9/2? Perfect. You guys get what to do though? Plug in 2, subtract, plug in -1, get 9/2. You can do it on your own a little bit later. I want to know if the setup's the key. The rest of us can be pretty easy, but the setup's the key. Show of hands if you understand the setup. Can we do another example? Truly, are you okay with it? You guys are so quiet. Goodness. Yeah. Mm-hmm. Okay. All right. Mm-hmm. I'm quiet. Let's see if you were just paying attention. Everyone in class right now, enough to do the double integral, yes or no?
No.
What's the most important part of doing any double integral?
Define the region.
Region. Setup. Man, you got to know the region. You got to get it set up correctly. By the way, I think I mentioned it earlier. I will always give your integrals on a test like that, with a region defined somewhere else. In a textbook, someone else's test, you might see a lot of this already set up for you. That's not me. I gotta make sure you understand how that works, because I was never taught that. That's a really bad way to do Calc 3. Okay, so you just don't understand what's going on here. So let me give you the region, and then we'll talk about it for a bit. So the region are all the ordered pairs on the xy plane that satisfy, some of you guys are zoning already, that satisfy the following conditions. I'm going to show you how to do this with a picture, and then I'm going to cheat. I'm going to show you that you don't need a picture to do it. You guys ready for that?
Yeah.
Firstly, could we draw the region?
Yes.
Could. True or false? The region would be on the xy plane. That's what this whole thing is about. It's about finding a region on the xy plane, so down here, shooting it upward, intersecting the surface, and finding the volume. So all the regions are on the xy plane for us right now. So this particular region looks like this. Well, if y is the square root of 1 minus x, that's a basic square root, which usually looks like this, but it's reversed. It looks like this. Looks like that. Yeah, I'm going to draw that a little bigger. What's y equals 0? What's that? What's that tell you?
X-axis. It's bound by it.
Bound by that. So this is y equals 0. This is y equals square root of 1 minus x. Shifted to the right 1 spot, 1 unit. Also, if you plugged in x equals 0, you're going to get that this intersects the y-axis at 1 as well. So our region is contained in here, but there's more. It also tells us something about the x. What's it start with? X equals
0.
What's that?
Y-axis.
And then x equals. What type of line is x equals 1/2? What's that give you?
Vertical.
Let's see if we can pick out the region. True or false? This region is going to be rectangular. True or false? Look, I need you to see this. Can you immediately see from the region that this that looks like it could be? But as soon as I go from something that is not constant, so even constant to a non-constant, I don't have rectangular any longer. I have some sort of other shaped region. Show of hands if you see that one. Now let's also check something. I see two regions. Which is the correct one? Is it the left or right?
Left.
This is the one that goes from 0 to 1/2 on the x-axis, and this is the one that goes from 0 to the function. This one also goes from 0 to the function of y, but we'd be failing the x part of that region. Head down if you're okay on that one. So the region we're talking about is this guy. I'm going to cheat and show you an easier way to do it besides drawing the picture, but I'm doing this for one reason. Please listen carefully so you don't miss it. Don't miss this. Please don't miss this. When you're setting up your integrals, you can do whatever you want, whatever order that you want to. You can go dx first, or you can go dy first. Here's what that means. If you put the dx first, that means that we're going to integrate in the x direction first, and then after that, don't write this down, I'm going to change it in a second, just watch. dx first, that means x direction along the x-axis in the same direction as the x-axis first, and then dy second between those two. Or you could do dy first and then dx second. That's the order in which you're doing your integrals. You're integrating in one direction and then in the other direction. Does that make sense? The dotted line I use as the second one, the solid I use the first one. That's my notation. It's not a textbook that just shows you what to do. It's a way to organize your thoughts. Here's how to choose. Because right now, hopefully you know they're equal. I talked about Fubini's theorem of non-rectangular regions in 14.1. It doesn't matter. You can switch things around. They're the same. So how do you tell? Here's how to tell. This is the big thing you need to understand. For my region, listen very carefully. Go in the direction along whatever axis is always between two functions and not switching between any two functions. So here's what I mean. If I go this way, this way first, between two functions, do you see it? I want the entire region between the same two functions. As soon as I change, that's not good. I don't want to ever have to change functions. So here, between two functions, between the same two functions. Are you getting what I'm talking about? I'm not switching lines. Between the same two functions. Some of you aren't even listening. You should be listening. Between the same two lines. Oh, is this same two lines? Yeah. Same two, same two, same two, same two, same two. What about those?
Oh.
As soon as that happens, that's a bad choice. Do not pick the dx direction first here. Because what would have to happen is right here, you'd have to have another integral. You'd have to do all this one integral, then add a different integral, and that is not fun. I don't want to have to be adding double integrals together. Does that make sense? I don't want to do that. Let's try the other way if this didn't sink in. Let's say I went the dy direction, along the y-axis. So dy along the y, it's called y simple. We'll talk about that in a minute. If I go this way, am I always between the same two functions of y for the entire region? Am I between the same two functions?
Yes.
Yes, between these two. I don't switch. That is what I am looking for. Did that make sense? Some of you guys, it's going to be hard for you to see. So take yourself, vertical lines or horizontal lines or whatever you have. Use a straight edge if you'd like. You got one here. And start imagining horizontal lines. And start counting the number of times you switch. If you switch between two different lines, that's bad. Don't do that. So here, this is the same two lines, the same two lines, the same two lines, the same two lines. Oops, did I switch lines?
Yes.
Did you catch it? I'll do it again. Follow these two lines up. Follow these two lines up. Am I always between the same two lines for the entire region? No, because right here, I switched lines. Did you catch that time? Some of you guys still don't catch that time. No?
Wait, where did you switch that? I know towards the top.
Follow this line up. Follow the whole region up. Do you see how I'm between these two lines right now? And then right when I get to here, does the region continue?
No.
Does the region continue?
Yes.
Am I still between these two lines?
No.
No, now I'm between these two lines. As soon as that happens, you need another integral because you've switched functions. Now consider this. Consider the vertical way. Notice how I'm between this curve and this line, this function. Does it ever change for the entire region? Do I ever switch functions for the entire region? Then that's the appropriate choice. That means I want you to do dy before you do dx. And we'll try some of these later on. We'll see how this works. But the whole key is, and you can draw it in different colors if you want to, draw out every different line that you have if you want to. So I'll use a purple line for this little one.
So when it hits the arc.
And I'll use maybe a blue line for this one. Now we're getting super crazy, but whoa! Awesome. The purple might be hard to see, but that's purple. Ready? If you switch colors, that's the wrong choice. Switch colors for the reason. Red and black. Red and black, 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 purple black. Oops, that bad. Don't do that. That means this. That means that going along the focus. Some of you guys are drooling. Goodness. Put color, you start tripping or something. That means that going along the x direction, doing dx first, not good, because you would have to switch functions. Make sense? Check this one. Am I always between the purple and blue lines for this entire region going vertically? Yes. Go dy first. That means along the y, do dy first. That's the appropriate choice. So let's set that up and I'll show you how to cheat. By the way, don't lose track of what we're doing. These things are always giving us not area. They're giving us what? This is volume. Over this region, under that surface. That's the idea. Okay. So, how I start these off, I'll always do my function first. I'll always determine, this is the order, guys. Listen, trust me, this is the order. Write down the function, determine this ordering, and then follow it up with the definition of your region on your integral, okay? So, which way do we want to go first? Dx or dy? Why?
Because
Because I said so.
the functions don't change.
Colors don't change. Because you're not changing between two different functions. It's always the same two functions. Show of hands, you understand that concept. That's a big deal. I never understood that. It's like, why? Why does that matter? It matters because it's easier to stay between the same two rather than have to switch. This way is great, this way not great. You're switching between too many functions. So, how you draw it? We're going to go along the y direction first. And then we're going to go along the x direction. Now, here's how to put your functions in order. Here's what you do. We always go from smallest to largest. So, if we're going along the y-axis, that's the dy, integrating along the y-axis. Where's that black line start? At y equals what? 0. Perfect. Where's that black line stop? At that function. Hey, is that function defined as y equals something?
Yes.
That's fantastic. Y equals what? Should things be okay with that one? You have to have this match up. Listen carefully. This dy must be what this variable is equal to. Well, this variable here has to match up with this variable. That variable's got to be a y variable here, a y value and a y function. Okay, now if you're okay with that one. So we're going to go dy first along the y direction, then we're going to go along the x direction. I represent that with a dotted line, signifying that's the second thing we're doing. Wrap it up with a dx. And then this is pretty easy. X is going between two constant values. Start here, go here. What's the x go to? Or what's x start from? X equals
0.
2x equals 1. I'll tell you something. Hopefully I'll make it easy for you. Whatever is on this outside integral must always be constants. Say that again. Whatever's on this outside integral must always be constants, because at the very end, you have to plug in numbers to get an actual number out of this. Does that make sense? You can have functions here, but here you can't, because you're going to have to plug that in and actually evaluate it. So let's double check everything. First, are you guys okay with the picture of the region? Show of hands if you are. Yes, no, yes, yes, yes. Okay, fantastic. If we want to get, I've already asked you too many times, I'm going to ask you again. We want to go dy in the y direction first because we're not switching functions. So we want to match up the y with y equals. We want to match up the x with the x equals. And we're going to double check that. Y goes from 0 to the function y equals square root of 1 minus x. X goes from x equals 0 to 1/2, 0 to 1/2. That's the proper setup. Show of hands if you're okay with that one. I'll give you another checker. Ready? Another check your worker. Whatever variable is here has to match up with the next variable. Think about y. We're going to be integrating with respect to y first, correct? We're going to be plugging in for y. Everything's got to change to x's. That variable, the second one, what's equal to, has to match that so that I can actually properly integrate. Does that make sense to you? And we'll see that right now. Oh goodness, we're ready to go. Can you try it? See if you, yes.
The outside integral, how come we don't have to do another integral whenever you're moving up to that?
That's a great question. I was
extra
hoping
line?
you wouldn't ask that question, but I'll answer it now. Here's why. True or false? I know it's true because I did in 14.1. Every region, rectangular or not, watch 14.1. Every region, rectangular or not, can be bound by a rectangle. Namely that rectangle. So, when we're integrating this way first, it holds us in here, but the x values still move between here and here the whole way. This is already taken care of for us. I'm just moving all the way up that rectangle, x, or vice versa. So if I did it the other way, I'd be moving along this whole rectangle, but it's already taken care of by that dy. Does that make sense? It's already limited. So the other one, the constants you don't care about, that's where we get that bounded by a rectangle idea from. Let's try it. What's our variable here when I'm doing my first integral? Come on, everybody, what is it?
Y.
Let's go ahead and do the antiderivative, but only with respect to y. Man, what's it gonna be? How would you do that? Say what now?
XY squared.
XY squared. So, what's this held as when you're integrating with respect to y? So we add 1 to the variable, power of the variable, divide by the new power, same stuff works, and simplify. So yeah. Man, you can always check your work, just do an antiderivative with respect to y, and you know that you're going to have the same exact thing. Are we done? Man, not even close. What's the next thing we do, everyone, quickly? We're going to start moving quick on the integration part of it. What do? Evaluate for what variable? The one you just integrated with respect to. So that's why we put y equals and y equals. Now we're going to evaluate. Where do we start? Y equals what, please? 0. And y equals? Write down everything I wrote down. That way you don't plug in for the wrong variable. Wrap it up with a dx. Yeah, it gets a little weird because we have this integral holding this stuff together. Don't let it confuse you. Get used to it. We still have one integral to go. Let's continue. I know I have x equals 0 to x equals 1/2 for sure. If I plug this in, where does this stuff go? In for the x or in for the y? That is why we write it. Tell me what I should have.
X minus x squared.
Louder, because I cannot hear you.
X minus x squared.
Oh, you guys are too fast. Okay. My brain does not work that fast. I want to show some work here. If you plug this into that y, it's going to be squared. You're going to get 1 minus x. Yes, you will distribute that ultimately, but we're taking this and squaring it. That's where that 1 minus x comes from. Let me know if you're okay with that. What about the 0?
Cancels out.
If you're plugging in y equals 0, you're going to get 0. And we still have dx. Oh my gosh, look. Look, this is why the variables have to match up the way they do. If I'm plugging in for y, it's going to let all the y's be replaced with functions of x. That lets me integrate later with respect to the same variable. So, variable here matches your first variable. Second variable, what you're putting into your integral, what you're evaluating for, needs to match up with your last variable. That's a big deal. Should we be okay with that big deal? Okay, let's continue here. And now it becomes pretty easy. So, as soon as we take care of that inside integral, we got something that's Calc 1. We get some pretty, or at most Calc 2. The main idea is, man, get your regions correct. If you get your regions right, and you get your setup right, you almost can't screw it up unless you start getting these things out of whack. Then you start plugging in wrong variables and your integral becomes impossible. Did anyone work that out and get something from that?
112.
Say what?
112.
112. Okay. So I got you. Ladies and gentlemen, I truly want, I know that some of you guys are tired, all right, I get it. I told you for the next couple days, I need complete focus, I really do. These are the big time lessons for this chapter. I need you here. I need you guys to be with me and participate. I truly need, this makes sense to me, man. I understand the region, I understand how to set it up. I understand that I can interchange x and dx and dy, but it's not a good idea to sometimes. I understand that I got to go between these two functions of y first, otherwise I need multiple integrals for the other way, and that's a bad idea. I understand that that's not my region, that's my surface over the region. Hopefully I understand that I need to go along the y first, therefore I need y equals first. I need to go along the x second, that means I need these functions to be only in x's, and these to be x values themselves, constant values, because when I evaluate this last integral, I need to be plugging in numbers to get out numbers. Do you understand all the things I understand? Now I'm going to show you how to cheat. I'm going to show you how to cheat. Cheating. Ready for cheating?
Yes.
Love it. Sometimes we get away with some cool stuff. Here it is. If you ever get a region where one variable is between constants and the other one is not, your choice is done. The choice is made automatically. Because if one variable is between constants, we just talked about it. You have to plug in constants last. Do you guys get it? You have to. So if one variable is between constants, that's the last thing you should be integrating. So if your x is between two numbers, do dx last. If your y is between two functions, do dy first. Does that make sense? That's a really easy choice to make. If you're between, well, rectangular, you get to pick either one. Honestly, I can't give you something that's between two functions here and two functions here and have you set it up from that. You'd have to draw a picture and find your intercepts and go that way. But if you're ever given a region between constants, put that as the most outside integral. Then you're done. Does that make sense to you, that logic? If you got to plug in constants last, make that the last integral you do. The outside integral, match up that variable with the d whatever, x or y, and then your inside variable is taken care of. You sure you're okay with it? Tell you what we're going to do. We're going to take a short break. We're going to come back. I'm going to show you Fubini's theorem for general regions, and I'll talk about that example I just referenced right now. What if I don't give you a predefined region between constants? What if I just say, hey, find the volume of this under the surface over the region contained by two functions? I'll show you exactly how to do stuff like that. So that'll be when we come back. All right, so the last thing you need to know before we start dealing with practically any double integral that we're going to have in our section here. And I mentioned it, but we haven't talked about Fubini's theorem for general regions. The idea, there's a lot of stuff on the board right now, like, oh my gosh, that looks crazy. Listen, let's break it down real simply. Please look. Here's what you know so far. What you know so far is that whatever variable's here, this must be this variable equal to a function in this variable. So listen very carefully. Whatever variables are up here has to match up with the second outside piece. Whatever variables are up here has to match up with the second outside piece. These numbers have to be constants because when I evaluate the last integral, I got to be plugging in numbers. Head nod if you're okay with that one. Fubini's theorem says it don't matter. It doesn't matter which direction you go across first, which axis you travel along first. Either the y or the x, it doesn't matter, provided you have the functions correct and the constants correct. The functions correct and the constants correct. So I want you to look at what these two scenarios say. In this scenario, we're bound by two functions y equals. Y would equal a function of x. Y would equal a function of x. That's what that would be. Look. What variables would be over here, x's or y's? X's. Y would equal a function of x's. Why x's? Because when I plug it in for that variable after integrating with respect to that variable, I've got to switch variables. I've got to have all x's for the last integral that I do. Did that make sense? I don't want to confuse you. Don't just nod your head if the answer's no. Be like, not really. Okay, let's try it. Let's try on this one. If I do dx first, I need to go along two functions that have x equals. I need to be traveling along the x-axis first. That's between x equals a function and x equals a function. Well, if I have x equal to a function, it's got to be a function in the other variable, in the variable of y. Does that make sense? So, we go, okay, along the x-axis, between two functions, x equals a function of y, x equals a function of y. Why do they have to be x equals a function of y? Well, if I have that, then these will all be a whole bunch of stuff with y's in them. Does that make sense? So when I substitute this in for the x's I'm about to create, it's going to create everything in terms of that variable y. And then I can go ahead and integrate again. Does that make sense to you on that one? Okay, now, let's do an example to illustrate this concept. I need to show you what these things actually do. here's one of the main things I want to get across to you. Firstly, let's pretend this is my region, so I have the region bound by y equals 2x. I've drawn it for you, and y equals x squared. I've drawn it for you. They clearly intersect. Let's go ahead and find the intersections just so we're clear on this. This one's pretty easy. Hopefully you see they intersect at 0, 0, and 2, 4. Yeah or no? If you didn't know that, you'd have to set these equal to each other. X equals 0, x equals 2, cool. And if I plug these in, y equals 0, y equals 4. That gives me the point 0, 0, and 2, 4. And now that you're okay with that one. Okay, so basic algebra, just finding points. Listen, guys, I'm not getting a whole lot out of you today. Are you with me on at least finding those points?
Yeah.
Now I want to show you this. Is this region rectangular? Can it be bound by a rectangle? Yes. Here's the whole point of this. If I can be bound by a rectangle, then all I have to do is choose to go between two functions along the x or two functions along the y first, and then go along the constants for the other axis. So let me show you. So here, verify that that rectangle contains the entire region. Yeah or no?
Yes.
You sure?
Mm-hmm.
Check this out. Check this out. Let's do our two setups. I don't know what function this is, so I'm just going to write f of xy, because I don't really care. My whole purpose here is to get you to do the region. Let's talk about doing dy first. If I say dy first, what variable am I traveling along first? Which one? The y-axis or the x-axis? So dy means along the y. So let's go to the region. This is my region. Let's make an arrow that's traveling between in the region between two functions along the y-axis. Head nod if you're okay with that one. That's what we're doing right now. We're going from here to here in the y direction. Head no. Head nod if you're yes, no. I did say like 4 things there. We okay with that?
Yeah.
Okay. Along the y, along the y. Did you get it? Now look at it. Is this going between two functions y equals? Now, I'm not getting through to you guys. I'm not getting through to you. Look at this function. Yes. Is this y equals some function here? Yes. Y equals what? Is this y equals some function here? So this is going between two functions. Y equals what? What's the bottom one? What's the top one? Check it out. This is what we mean bound by two functions y equals. This region is bound by y equals x squared and y equals 2x. We go along the y-axis between two functions of y. Does it make sense? Now the variable switcheroo, if I plug in this for y, I'm going to be plugging in x's. It's got to match up with the second thing we're doing. That's the variable switch. So this variable has to match up with whatever variable we have equal to something else. If you really just want to make it make sense to you, just match up these variables with the second thing. Make sure you're plugging in for whatever that variable. Make sure these ones equal this. You have to plug in so that you get this variable everywhere. Now, let's talk about the x direction. If we go along the x direction now, we don't have to worry about being within the function. That's already taken care of. This along the y-axis goes along the y-axis for all of this stuff. Now I want to go along the x-axis. Well, those have to be constants. So all we got to do is figure out what the constants are along the x-axis. So we did y first. Now we're going to do x. But I'm traveling between my constants. That's where the rectangle idea comes from. So what's the outside of the rectangle? Where do I go from?
0 to 2.
0 to 2. Let's make sure it matches up. Does my y have functions of y equals something in x? Yes. Does my dx match up with x values of our region? That's fantastic. Now, what if we switched it around? So this is option number 1. I'm going to erase this, do option number 2. What if I wanted to go dx first? What if I wanted to go dx first? Would I have to change anything about these functions to do dx first? Because in order to do that, I've got to have x equals and x equals. It's not a problem. Just solve for a different variable, and then we can go whatever axis we want. So dy says along the y first, you have to have y equals, I don't care, a whole bunch of crap. But it's got to be y solved for y. Does that make sense? If you're going to do dx, you got to have solved for x. We don't have that, even though they're the same two functions. So if we do, this function would be what?
The top one or the bottom one?
By over 2.
So this, or x would equal
Square root of y. Right.
Now, it gets a little weird. You kind of have to turn your head like this and look at it, because we're going to go not from bottom to top, but from left to right. So from left to right, what's the furthest left function? Oh man, I hope you can get this right. If you get this right, I know you know what you're doing. What's the furthest left function we're dealing with? Because we're going this way. We're going along the x-axis with respect to x. It's choosing this direction first. We've got to go between two functions, but they've got to be x equals, and it goes from smallest to largest. So which one?
So we have y.
That one. That's the leftist one. Does it make sense?
Yes.
What's the furthest? Well, look where the arrow travels. The arrow travels that direction, correct? It starts at this function. If we're going along the x direction first, we need the x equals version of that. X equals y over 2. Where's this arrow end? Come on, where's it end?
Square root of y.
So the arrow ends at this function, which was the x equals square root of y. Show of hands if you're okay with that one. Now, yes, no? Okay?
Yeah. Disregard what I said.
What are those numbers? Everybody, what are these? Where do we go from here to here?
0 to 4.
0 to 2?
0 to 4.
Why?
Because we have to go along the other
Exactly.
direction.
Why? Because if we're going along the y, this part's second. I've already integrated this direction. I've gone between my two functions first, and now I want to wrap up this entire region from here to here. The rectangle contains this, but in the y direction, it's 0 to 4. There's a lot behind that. We're going to practice a lot of examples. We're going to go pretty quickly. We're going to practice a lot of examples, but I need you to understand the basic concepts. We've done the hard part already. This is the end of the hard part. Now comes the easy part, but there's a lot behind here. There's a lot of stuff that we've just unpacked today. Well, if you want the recap, here's the recap. Rectangular regions are pretty darn easy. Make sure the x bounds match the dx. Make sure the y bounds match the dy. Don't matter the order. Sometimes it makes it easier. We'll find that out in that example. Are you listening? Some of you guys are not. You need to focus. Next, if you're ever going between two functions, like this, the region that's just bound, you need to figure out where those things intersect. Because what that does, what our intersection does, is creates this rectangle for you. Choose to go along one axis first. Listen carefully. If you're going to go along the y-axis first, focus. If you're going to go along the y-axis first, you need to have those functions y equals. Does that make sense? You have to have that. If you're going to go along the x-axis first, you have to have the functions x equals. You have to have that. That's why we write this y equals. So y-axis first, y equals. X-axis first, x equals. That should make sense, because after I do my first integral, I'm going to be plugging in a whole bunch of x's. With me? This is going to be gone. I'm going to have dx's. I need everything to end in x's now. If I plug this in, I'm going to have a whole bunch of y's. I need it to end in y's, because this is going to be gone. I need everything in terms of y to integrate with respect to dy. The constants are the easy part. The constants just say, hey, what's creating the bounds of my rectangle? The bounds of the rectangle that contains my region. That's pretty easy. As long as we do function first, the constants are either along the x or along the y, and then you're done. Just match up those constants with the last d whatever. So dx along the x, dy along the y, and that's the last thing we do. Is that clear for you? We've covered everything. This is everything you need to do to appropriately do double integrals. Now we get some practice. Like I told you before, we're going to move quickly. The focus I have here is setup. All about the setup, because that's the hardest part. Yeah.
Is the function on top with respect to y normally switch if you start with x first, or is that just coincidental in this example? So say on the,
Why we switch these things?
no, like say on the first one we had y equals 2x for the upper, and then it became the bottom on the with respect to x. Do they normally switch?
Yeah.
Okay.
Because going from low to high here is going low to high this way. They typically do switch.
Okay.
I don't know if they always have to, but I think so. I'd have to think about that for the always. So the question was, if you didn't hear it, this one started 2x on the top, and then when we solve for x, we put it on the bottom. Does it happen a lot? Yeah, it does. Because if this is low to high, then if I go left to right, the high is typically, it doesn't have to be the left. It could be different. If these were switched, it would be different. You just have to look at it. You just have to go low to high, or along the x, left to right. It's the best I can explain it for you. You guys ready for some practice? Let's talk about this one. So first thing I'm noticing, hey, is this representing the region? Yes or no? Okay, so we have a region. We're going to have to define that. Can you choose to go dx or dy in either order and be okay on any integral, like whatever?
Yes.
For sure. What type, everyone in class right now, what type of region do I have? Rectangular or non-rectangular?
Rectangular.
For sure. So I can set this up however I want to. Actually, you literally can't mess up the setup. Tell you what, I'll do it for you. I'm pretty sure that we're going to go from 0 to 1 and 0 to 1. For sure. All right. For sure about that. Yeah, for sure. That's not what I'm worried about. What I am worried about is whether we're going dx or dy first. By the way, do you have to draw the region every time? No, you don't have to do that. I've shown you some ways to get around that, and I'm going to show you some more. That's what our examples are for right here, showing you ways to make this stuff as easy as humanly possible, for the most part. Does the setup matter here?
Yes.
The setup always matters. We're going to pick the setup that makes it easiest. So watch. Here's how to set up to make it easiest. Please watch carefully. Suppose we did dx first. Don't write this down. You just need to focus, okay? You just put pencils down if you want. If we did dx first, what would our first variable be? What would we integrate with respect to here? Do you know? Okay, so let's pretend. Do you know how to do this integral where x is your variable? Okay, would it be easy to do?
No.
Then probably don't choose that. Because if I did this, I have x over 1 plus xy with respect to x. Imagine this. If that wasn't there, would you be able to do that integral? The answer is, okay, how? U sub? Derivative of 1 plus x is 1.
Watch your videos. Watch count videos.
Partial fractions? Nope. You could split it up. You could do x plus 1 minus 1. So you get 1 minus 1 over x plus 1. That's ln. You could do that. You could have x minus ln of 1 plus x. Think. You could do that. Here? Yeah. Still work out pretty much, but that's not easy. Now, let's try to make it, let's see. So can we do it? Maybe. What if we switched it? What if we switched it? Would it get easier?
Yes.
What's the derivative of this with respect to y? Do you remember anything about u subs? What's the derivative of this with respect to y? Oh, good lord. Oh, my goodness. What's the partial derivative of this thing with respect to y? What's the derivative of 1 with respect to y? What's the derivative of this with respect to y? Is that anywhere else in your integral? U sub. Set it up so that you can do easy stuff. I'll give you a pointer, okay? You get to choose whatever setup you want. But if you set it up and you're like, oh my gosh, like hitting my head against a wall, kind of like talking to you guys sometimes, you're all zoned out like this. Oh, wait, I'm sorry. What was that? Look, if you set this up and you're hitting your head against a wall and your integral's just not working, just switch them. Switch it around and see if it works better. For instance, like this week, okay, hey, if the x was first, that sucks. If the y is first, try a u sub. Let's try a u sub right now. Now, real quick, I know it doesn't matter because it's 0 and 1. What variable is this equal to? Oops, I gave it away. And that's y. And this would be x, and that would be x. Head nod that you're okay with that one. Okay, do you need to write them? No, it's just something that I have for you. So let's try it. Let's do a u sub. U is the opposite of a chain rule. A U sub is opposite of a chain rule. It's almost always a composition. It's usually the ugliest thing. Here it's the ugliest thing in the denominator. Now we're going to take a partial derivative. We're going to just put a du, but we're just any other U sub works the same way. So du is what now? Oh, yeah. D what? So we better have some better notation. We're going to do a U sub where y is our independent variable. We're going to have that U sub equal to 1 plus xy. And then our partial derivative with respect to, oh, that makes a little bit more sense. Now we're taking it with respect to y. So we're going to show that stuff. Equals x dy. Because we took it with respect to y, we're going to show that. Head nod if you're okay with this idea so far. Now, hey, I see that part right here. That tells you this U sub is going to work. Does that make sense to you? Also, I want to show you substitutions still work. What can you do every single time you do a U sub with actual bounds? What could you do? Changing bounds still works. You don't have to do it. I like to do it though. It helps us out a little bit. So we can also change bounds. Here's how changing bounds works if you don't know. It's why we write this stuff right here. So if I change bounds, y equals 1, it's going to change your functions though. Y equals 1 means that u is going to equal, well, use it. Use your substitution. That's your rule, right? That's your breadcrumbs to get back to where we're going. So if y equals 1, what's the u going to be? Did I lose you? Take your y. Do you see where the y came from? Right here.
Yes.
Take your 1, plug it into your substitution for what variable? Is that changing? Is that changing? Is that changing?
Yes.
Plug it in. What do you get? What if y is 0? What's our u become?
1.
We can still change bounds. Okay, let's rewrite it. Bless you. What's my integral start with? The outside integral, is it still 0 to 1, yes or no?
Yes.
This one. Did I change anything about that? My inside integral, did I change anything about that?
Yes.
Changed a lot about it. I'm not doing dy anymore. I'm doing du, so that everything's going to have to be in terms of u. So where's my u start? I'm going to put u equals 1. I'm going to put the u. That way I know I'm going to be substituting for that variable in just a second. Does that make sense to you? And then u equals what, please? Okay, let's really focus here. How does this change? What's this going to be? Am I still going to have this x dy? Come on, folks. Help. I need more out of you. What's this x dy going to change to? Good. We're going to do du, but yes, du. Over, is this still going to be here? This 1 plus, what's that going to be? du dx. You always have to make sure that that variable is the same as the one you have equal to something else. And what you have here needs to match up with the outside variable. It still does. That's why we change bounds, to make it nice. You can do it without changing bounds. But remember, whenever you do the integral, you have to change back into this and then plug in numbers. You're doing the same thing, it's just in a different order, just like Calc 1 and Calc 2 when you did these things then. Are you guys clear on this stuff?
Yes.
For sure. Let's continue. I still have an outside integral. I told you we're going to be moving a little quick on this. Focus here, everyone in class right now. What's the integral of 1 over u with respect to u? What is that?
The absolute value.
I'm still going to have a dx. However, before I do that, I've got to do what? Come on. When I evaluate it, hey, what variable am I going to be plugging in for?
U.
From what values?
1 to 6.
Write down all the stuff that I just wrote down. Write that stuff every time you do one of these problems, because we're switching variables a lot, right? Plugging for a lot of different stuff. Write that stuff down. Head nod if you're okay with that one. Now let's actually evaluate this thing. So we're going to have integral from 0 to 1, no problem. What am I going to have when I evaluate ln of absolute value of u? What do I put in there?
1 plus x.
And 1 plus x.
So ln of what?
1 plus x.
Minus ln of...
1.
I can do this for you if you want here. We'll talk about why that doesn't need to be there in a second.
Right.
Okay, listen, I know this is brand new. I know that we are just trudging through some material, and I know that this class just got real for a lot of you. You're like, whoa, crazy. This is new. You're right, it's new. There was a reason you took Calculus 2 after you took Calculus 1, and why you had to take both those classes before here. It's so that when we get to freaking integrals, you actually know what you are doing, okay? There's a reason for that. I have a whole 3 terabytes of videos on Calc 1 and 2 terabytes of videos on Calc 1 and 2, because they're big-time classes that you need to understand before you get here, okay? So if that's lacking, take some time, watch that, go back through your notes, try some examples, okay? Here, we're moving. Here's the big ideas I want to walk through one more time to make sure you're with me, because I'm hopefully with you. This ain't your region. This is. Rectangular regions don't care about the setup, but you do. Because how you set up your dx or your dy matters. Sometimes we get really hard integrals that if we switch them around become really easy. Here that was the case. We do dy first, we have a basic u sub. So we're going to let u equals this, no problem. The derivative is this. That's our substitution for du. This becomes u. Change your bounds, man. It makes it easier. At least a little bit easier. How you change bounds, you always use your substitution to change bounds. Plug in whatever your variable is. That's why we write the variables, guys, so you know what to plug in for. If you don't have this up here, you might plug in for x. If you do that, you just change your bounds incorrectly. Does that make sense? Always match up y's with y's, x's with x's. That's a big deal. So when we plug in 1 for y, we get 1 plus x. When we plug in 0 for y, we get 1. That just changed our bounds. We're now no longer in y's, we're now in u's. Hey, the u's match up with the du. That's gotta happen every time. These are still x's, that's still dx. And notice, when we take and do our integral, it's basic, it's just ln of absolute value of u. We now get to plug in for u, and everything's gonna turn into x. Just like what we want. Does that make sense? Hello, yes, no?
Yes.
Okay. So when we plug in, we do the 1 minus x. Now, look back at your bounds. Because x is going from 0 to 1, this can never, ever be negative. Do you see that? We get to drop the absolute value. So this doesn't have to be here because of our bounds in terms of x. Also, when we do, so let's see. How much is ln of 1? At this point, I'm going to make a statement to you. I do not care how you do these integrals. I really don't. Back in Calc 2, I would have cared. Calc 1, I would have really cared. I don't care, man. You can use a table. You can use a calculator. You can just do them in your head. I don't care. We're past that. We're way past just trudging through integrals. However you can do that integral, you do it. Me personally, I've memorized integral ln x is x ln x minus x. That I've memorized. So here, because it's a basic u sub, the derivative of that is 1. I'm going to get 1 plus x ln of 1 plus x minus 1 plus x. I don't care how you do it, man. U subs, whatever. But just make sure that you can do all these integrals. It almost sounds harsh, but I don't have time to reteach you integrals. Now, are we done?
No.
Oh, we're so close though. Let's wrap this thing up. What's the last thing that we're going to do? Come on. Plug in for, oh, what variable? That matches up. I kind of dropped right into x, but you could write it the whole time if you want. X equals 0 to 1. So we're going to evaluate for x. We want to make sure our variables always match what number we're plugging into, or what variable we're plugging into. That's true, it does here. If you plug that in, you get 2 ln 2 minus 2, and then minus 4. Plug in 0. I think I got ln. That. If you plug it in, work it out, 2 ln 2 minus 1. Sometimes you're going to see some different stuff. You know this from like your Calc 2 days, or Calc 1 if you had early transcendentals. A lot of times when you do integrals involving ln, your answers look a little different. You can take that as an exponent if you remember your ln rules. Just please, I'm begging you, please do not subtract 1 from that 4. Begging you, please. You can move powers, but you can't start subtracting weird things. Okay, we're going to practice a lot more, as many as we have time for. I want to know one thing. Is the setup okay with you? And do you understand why we did dy and not dx?
Yes.
Okay, we're going to move on. Nice, right? Nice. So let's take a look at it. Double integral for sure. I'm giving you a region. Here's what I want you to check. Well, you know what? Write it down, then look up here so I know you've written it down. I don't want to talk over you writing, okay? That way you can actually focus. Hey, here's a question. Do I always have to give you a region for you to do an integral setup like that?
Yes.
So look at the region first. Does this give you the region? No, that's the surface over the region. We're finding the volume under that surface over that region. So let's look for the region. Now look at the region before you do anything else. Before you do anything, look at the region because this is how you cheat. You look at the region here for rectangular, it says it don't matter. So pick the easiest way. You look at the region here. Hey, is that rectangular? No. Whoa, how about this one? Is one variable going between constants?
Yes.
You're done. If one variable is going between constants and one is not, let's think about that. You know that the last integral you do has to go between constants, right? Okay, let's get that right. The last integral you do has to go between constants. It's got to. The first integral you do could go between constants for rectangular, or it's got to go between functions. Does that make sense? So let's do our setup here real quick. So let's take a look at it. This is how you cheat, man. You don't need to draw the pictures. You only need to draw the pictures if you don't know what you're doing. Or if you're going on a region that's bound by two functions and it's not explicitly going between constants. So this is really nice if you're given a constant bound for one variable. That's a really good thing. So let's check it out. On this integral, do I want to end with dx or do I want to end with dy? You tell me.
Yes.
Why? Because I need the x's to be, I need the constants to go last. If the constants go last, that's the last integral that I want to do. Does that make sense to you? Can you see what I'm trying to do here? Try to get you to do.
Yes.
Guys up front, yeah, no? Left-siders? Okay. So I know that x has to go from 0 to pi. That's a must. Now let's check this out. What's that one got to be? I need y equals. Oh, what's the lower bound going to be?
Negative 2x.
And even though it looks worse than that, this is an easier case. It's easier because you can't set up this integral any other way unless you want to draw the picture of the region and start switching around functions. Does that make sense? This is the easiest case to do double integrals, where the region is one variable is bound by constants and the other one's not. Deb, listen, I don't believe you that you fully get it. Do you? So 4 hands go up. Okay, I did something wrong. I don't believe that you fully get it. I don't, because some of you guys are just kind of going, eh. Some of you are like, yeah. Some of you are like, okay, that's bad. But I don't believe that you fully get it sometimes, because I want to know if you understand the concept of if I give you a variable between constants, it's your last integral.
Yes.
Do you get that idea?
Yes.
If I give you a variable that's bound between a function, that's your first integral. So if I look at this and go, hey, x is between constants, man, put it last. Put it on the outside integral. Y is between two functions, that's great. It gives you the lower function. It gives you the upper function. Make that your first integral with respect to whatever variable is bound between functions. Now think back to the Fubini's theorem. I said that the first integral has to be between y equals and y equals. Let's see that it matches up. Does this variable match up with my dy?
Yes.
Do the variables in the function match up with the next thing I'm going to do?
Yes.
So that when I plug in, I have all x's. That's what I want. And then I plug in the values for x, and we're good. Do you want to try it?
No.
Yeah, too bad. Do it anyway.
You said.
if you're fast at this and you're pretty quick and you want to try the setup, we're just going to set up the next one. We're not going to finish it. I just want the setup. The setup's the most important thing, okay? So if you finish this and you want to try to set this up. Hey, ladies and gentlemen, to get you started, what is my first variable in here? Is it x or is it y? Okay, so what would you do to do the integral of, oh man, there's not even an x in there. That's kind of nice. How would you do the integral of ln y over y? U sub, what is your u?
ln y.
Perfect. And this is with respect to y is my variable. I make a little note with that to make sure that y is my variable I'm working with here. That gives me the dy over here, that to not get confused with the dx. That gives us our substitution. Also, hey, could you change bounds? Yes. This would be a good idea to do. Look at why it'd be a good idea. If I put an e to a cosine and e to a negative 2x into an ln function, e and ln are gone. That's really nice. So if we change bounds, the first one would be y equals e to the cosine x. And here we'd have y equals e to the negative 2x. Separator. If that's the case, I can make it really nice. So if y equals e to the cosine x, we have ln of e to some power. Ln next to e, gone, we get what, please? If I put this in for ln, so here's our y, use this substitution as a pattern for getting to change bounds. Put in e to the negative 2x, ln of e to the negative 2x gives us what? Put them in the same order that you got them from. We still have two integrals, but everyone in class right now, tell me what variable I'm switching my y's into. What's it going to change to? So instead of y equals e to the negative 2x, that is mapped to u equals negative 2x. And instead of y equals e to the cosine x, that's mapped to u equals cosine x. Also, we did a whole bunch of work here. Help me out with this right side, people. Come on, I need a lot from you today. What's this going to look like when I've done all my substitution? What is it? U, this is now u. This part is the du. Double check your work every time you do something. Make sure your variables match up. So, does this variable match up with this variable? That's great. It doesn't have to. You could have some x's in there, but you can't have any more y's, all right? Does this variable match up with the things you're about to plug in for? Yes. Does this variable still match up with the last thing you're doing? That's how to check your work. You got to make sure that you're all set, you're going down the right path, so that we don't get halfway done and go, oh man, I messed it up. Hey, in the hardest integral ever, what's the integral of u? Do I immediately evaluate with respect to x right now? That's crazy, because that's the wrong variable. That's why these variables have to match up. The ones that we're equal to have to match up with the next thing we're doing. We got to substitute for this variable these things and change our function around. So we're going to evaluate for this. Get some nice stuff out of it. What we end up getting get the same thing I did. Something along those lines. With me? You could, yeah, absolutely. You could factor the 1/2 out. That's not a problem. Again, I'm not focused on the rest of this problem. I'm focused on your ability to understand a couple things about it. Number one, y'all feel comfortable getting the setup from here to here. It's the biggest idea. Can you do the first integral and plug in the values for it and get down to here? As soon as you do that, you've just managed to change a Calc 3 problem into a Calc 1 problem. Maybe Calc 2. Maybe Calc 2. It doesn't have to be. You do it with a U sub when you do this part. 1/2 1 plus cosine 2x. Basic U sub. You get me? This one's super easy. Tell you what I want you to do. I'm not going to finish these things for you. Look, would you know how to do that integral on your own? Yeah or no?
Yes.
Do that. Be a 1/4. Can you do that integral on your own? Try them on your own. I'm going to get you this far on the rest of the problems. I'm going to get your setup. I'm going to get you your first integral done. And then I want you to try this on your own to make sure your integration techniques are still up to par. Here's the answer that we're looking for. You can see where the pi cube's coming from because you're taking x to the 3rd power. Hopefully you can see that we're going to get some stuff from that with an x. Combine some like terms there, and then you'll be able to do that one. I'd like a true show of hands if you feel okay on the setup and the first integral. Show of hands if you do. That's darn near everybody. That's fantastic. Any comments or questions before we move on? You ready for the next one? Next one's fun. So you're ready. Do you understand that one? Then you're ready. Tell me the first thing that pops out of you with that problem. Come on, first thing that pops out of you. What is it?
Double integral.
Yeah, it's a double integral. Fantastic. Yeah, it's a room in that section. Very good. Thank you for that comment. Very useful. Where's the first place you look? The region. Tell me something that pops out of you about the region.
It's rectangular.
It is rectangular, for sure. So, let's set up the double integral. Tell you what, it's a hard one. I'll do it for you. Yeah. You're welcome. I know. Got my important belt buckle on today to do important work like this. Superstar. Superstar. Yeah, that's not the hard part. The hard part is, which one do you do first? Let's talk about it. I know that I don't change this around, but I want to think about whether this is dx dy or dy dx. Do we go in the x direction first, the y direction first? I don't need to draw the region, it's just a rectangle. What I look at is, would there be one way to make this easier? Well, let's try. What if I did dy dx? If I did dy dx, y would be the variable. Are you following me? This is a good. I'm trying to model the thought process for you so you can make correct decisions when you're doing this on your test. If I choose dy, this doesn't switch, but if I choose dy dx, y would be the variable, and I would have this as a variable and that as a variable. I would have a product of two functions that have the variable in them, correct? This would be by parts. Maybe. Maybe we want to do that. Let's check the other way. If we did dx dy, what would the variable change to? What's the variable now? How many variables do you have? One. What's the derivative of this with respect to x?
Y squared e to the x squared.
Just this part.
Or y x.
Okay, let's try this. If u is xy, what's the derivative with respect to x?
Y. So we'd have to do
Oh, this would be a by parts? U sub? Yep. Pick the easier one. Pick whatever way is easiest. Would you rather do a U sub or a by parts? By parts, for sure. With trig subs in there and part fractions. Go. Maybe if you have to. But look, hey, if there's a way to switch this around and make your integral easier, do it. This is not the correct path. This one, that's the correct path. So let's do dx, dy, because here's why. If we do that, and we pick u, remember our variable here is x, to be xy, the derivative of u with respect to x is simply y dx. We took it with respect to x dx. Head nod that you're with me. Do you see the idea here? The idea is this piece, yeah, it's split up, but it's there. So we'd have 0 to 1. Yeah, you'd probably change your bounds. If x equals 1, u becomes y. If x equals 0, u becomes 0. So if we do it this way, we go, hey, let's let that be our u. No problem. No problem. Our derivative is, with respect to x, is y dx. Here's our y dx. This piece becomes our du. If we change bounds, x is 1, well, that maps to u equals y. X is 0, that maps to u equals 0. That's why we go from 0 to y. Our u's match our u's, our variables next match our next variable, and we have e to the u. After this part, can you all do this integral? That's pretty easy. This integral is e to the u. You plug in 0, you plug in y, subtract them, you're going to get e to the y minus 1, then do an integral with respect to y and plus numbers. That's the idea. The setup is important, but once you get here, man, you guys can all do it. Should be okay with that one. Okay, tell you what, we're going to do one more. I want you guys to set up and try this entire integral. I'm going to give you a couple minutes to set up, and then I'll start going step by step through the integral shortly after that. You guys understand what's going to happen? Try it. Pretend this is a test. I know that we've just learned some of this stuff, but we've learned a lot in the past hour. Let's see if you could do a setup on a double integral right now. I think you can. By the way, are these going to take some practice? This is some of it. It's called guided practice. Typically, I would walk around the room. It's a lecture hall. I can't. But don't ignore this. Sometimes I give you time to do problems in class. Don't wait. Don't wait for me. Even if you get completely the wrong answer. Learning from your mistakes is really, really important at this level. Okay, you got to try it. So try the setup on this integral. Okay, you have enough to set it up. Let's see if you were paying attention. Let's see if you can set this integral up without a picture, in the correct order, matching up the variables, making sure it's going to work. If you do that in shorter than the time I have that I'm giving you here, try to actually do it. See what you get out of it. See if you can do at least the first step. Have you set this up yet? Have you tried? Do you have a dy first or a dx first? What variable is bound by constants? That should be the last variable that you have. That should be the last integral you do. So what should you have first, a dy or dx? You should have a dx first, because that's the variable bound by functions. The variable bound by functions, first integral, inside integral. Make sense? Variable bound by constants, outside integral. So when I'm looking, I go, hey, that variable, 1 and e, those are constants. I'll tell you right now, if that's constants and this ain't, then this right here has to be the first integral, the most outside integral. It's the last integral we end up doing. That's the last thing that we do, is the stuff with the constants in it. Does that make sense to you? Yes.
Can you repeat that?
Sure. So when we look at integrals, you got a couple choices. Number one is you have a rectangular region. If you do, you actually have to think about what's easiest. If you don't, there's two cases for that. Either you're bound by functions, which we kind of got to that a little bit, or you're bound by constants in one direction, either one, and functions in the other. That's the easiest case. This is the easiest case that I ever give you. Here's why it's the easiest case. You know that the last integral you do has to be constants, numbers that you plug in, correct? You know that the inside integral could be functions to plug in. So if I do this, if we do that, let's just look at that for a second. This says that you do an integral, you plug some numbers in, possible. But then you do another integral and you plug in variables at the very end of it. Is that going to come up very nice for you? Not if you want a number that represents a volume under a surface over a region. You can't do that. Let's go the other way. Let's go this way. Can you do an integral and then plug in functions of some other variable? Sure. And then could you do another integral and plug in numbers and get out numbers?
Yes.
That's the way to go. So when you have a region that's bound by constants for one variable, that variable, d that variable, should be the outside. When you have a function, when the other function is bound by variables, d that variable, x, should be the inside. So x would go from y to y squared, y would go from 1 to e, 1 over xy. Did I explain that well enough for you on that one? You guys? For real? Did you try it?
Yeah.
What'd you do? It's easy to make a use of. It's easy to make that. It's not going to work so well. You could, but you're going to do the same thing as, actually, it's going to kind of be doing the same thing. Well,
Yeah. Unnecessary.
what's your variable? What's your variable here? So y is a... What if I thought about this as 1 over y times 1 over x? Is that the same thing?
Yeah.
Hey, like 1/7, like a constant. What's the integral of 1 over x dx? ln
Times constant.
ln x, right? ln absolute value of x, but ln x. But wait a minute, what do I do with the 1 over y? That'd be like this, folks. Hey, if I had 1/7, man, our only variable is x. If I had 1/7, 1 over x, I'd expect you to get 1/7 ln x. Does that make sense? I had the same thing. It's just y is being held constant. That's the idea for this integral equation.
Can you move the one on the y outside?
Sure, but only right here, not here.
Yeah.
Here, yeah, you can move it up for that. It's a constant. You can do it as long as it's not that variable. You're good. Now, I don't like to see it often because sometimes that 1 over y does play into a u sub. Okay, so sometimes we use that to eliminate that variable. It's real nice, but you can do it. It's possible. Is this making sense to you? Also, when you plug in the variables, you have to notice where that y went. Okay, so if you're going to do that technique, you be real careful with it. So here we're going to go from 1 to e in terms of y, but here we're going to have 1 over y ln absolute value of x. Y'all okay with it? For sure. Okay. Come on, then lead me. Lead me. What's the next thing I do? For what variable? That's why we put this. So you know I'm having x equals y and x equals y squared. That's why we put that. We integrate with respect to x. X was our variable. X is the variable I'm plugging into. And I'm going to replace every x with these two things. Head nod that you get me on that one. That's an important concept. Also, I want to make sure that whatever variable I'm putting in here matches up with what I'm about to do. I want to make sure that I'm going to put in a whole bunch of y's, and I'm going to have a dy to take care of the rest of that. So we get our 1 to e. It's in terms of y. You can write that if you want to. We have 1 over y, and then we have ln y squared minus ln y. dy. I want to see if you guys are okay with it on the math on that one. For real. If you're worried about the absolute value, I want you to look at what the bounds for y are. Y is always positive, therefore I don't need the absolute value because y squared positive, but y is also positive, so I get to drop those. You watch your bounds and you can do stuff like that. For real, head nod if you're okay with that one. Now, before we get all crazy and start doing like tons of other stuff, let's be smart about this. Let's simplify some of these pieces. There's a couple ways we can do it. One way that, probably the simplest way I would do this, you have ln of y squared minus ln of y. Do you know that you can put those together? That creates 1 ln of y squared over y. You can simplify that. Ln of y. If you don't like that method, move this 2 to the front. That's 2 ln y minus 1 ln y. That's still ln y. It's the same thing. You have 2 of them minus 1 of them, you got 1 of them. Either way, this piece is ln of y. Can you please tell me, everyone in class right now, what is the next thing you're doing on this integral right here? What's the next thing you're doing? You've actually already done in this class, yeah? What's the appropriate choice for you? Come on. So the derivative is 1 over y. That's gone. You just have integral of u, so you're going to get a 1/2 u squared. Change your bounds. And the answer here is 1/2. I want you working on your own later. This whole thing works out to 1/2. Try it a little bit later. We're going to do one more setup. I want you to get this set up. We're not going to finish the problem. This is going to be on your own sort of problem. I want to show you the setup, and then I'll give you the answer to it. But this is the last thing we have for this section for today. please don't answer this out loud right now, but I want everyone thinking about it because I'm going to have you answer it out in just a second. My question to you is, should we be doing this integral dx dy or dy? Take about 30 seconds. Look at the region. If you have to draw it, you can draw it, but you don't have to draw it here. Look at the region. Think about what it means. I'm trying to get your thought process to change. So you picture the region. Think about what's going on. Think about constants. Think about functions. And then make the appropriate choice here. I want to see if you can do that. Take 30 seconds, just think for a bit. Maybe some main ideas you have here that you should be thinking about is there one variable that's bound by constants? Is there one variable that's bound by functions? That makes your choice. So think about the appropriate choice. If you can't, if you're like, oh my gosh, I don't know what I'm doing, then you gotta draw. Then you gotta draw a picture. We'll get to that. Okay, I've given you about 30 seconds here. Hey, is there a variable that is bound by constants?
Yes.
Okay. Is there a variable that's bound by functions? So what's the first one I should do? dy or dx? Constants outside. So functions inside. You said it's dy, correct. It needs to be dy, then dx. Now let's fill this thing out, and then I'm going to give you the answer to it. The x's have to go on the first integral, yes or no?
No.
The x's go on the outside integral.
Yes.
What's the smaller of those two x's?
0.
They have to go in this order. The bigger of them? Okay, now this can trip some people up. I know y goes between 0 and cosine x, but you got to know which is the bigger and which is the smaller for this region of x from 0 to pi over 2. Oh, you know some trig. Yeah, great, okay. So plug in some numbers here. What's going on this interval of 0 to pi over 2? What's going on here? When I plug in numbers from 0 to pi over 2, is this larger than 0 or smaller than 0? That's all you got to know. It's larger. So y is going from 0 to pi over 2 to cosine x. Does that make sense? On that interval. If you had to draw it, cosine starts at 1. It basically drops. So here's y equals cosine x. Here's 0, y equals 0. We're going to go this way first, dy first, and then we're going to go along here. That's the idea. That's the picture of that region. That's what we'd be doing. Do you need the picture? No. Not if one variable is bound by constants. That's just your outside integral. And if one's bound by functions, just, man, hey, tell you what. These variables better be these variables. Take these numbers and start plugging them in. Start plugging something between here. If I plug in like pi over 4, that's root 2 over 2. That's 0. I know this is bigger than this for this stretch of the x-axis. Does that make sense? That's what we're doing. We're going along the x and along the y. By a show of hands, how many people understand why we put dy first and dx second? It's the biggest idea. How many people understand now why 0's here and cosine x is here? What if this was between pi over 2, pi over 2 and pi, which would be, what if this was pi over 2 and pi? Would this still be in the same order? No. You'd switch it because cosine x would be less than 0 for that. Does that make sense? Then you got it. The first thing you would do is dy, y would be your variable here, correct? So what's the integral of sine, that's a good one. What's the integral of sine x with respect to y? Y sine x. What's the integral of y with respect to y? You guys with me on that one? Then we plug in, what variable would we plug in for? Check it out. Y would get replaced with cosine x first, and then y would get replaced with 0 second. The zeros, everything's going to be gone. Verify that everything's going to be gone for the zeros. So this function would become this. X goes from 0 to pi over 2, but then we'd have sine x cosine x minus 1/2 cosine squared x dx. Look at the beauty of this thing. If you do it right, if you set it up, if you plug in for your variable here, you're going to get all the second variable only. And then you can do integrals like Calc 1 or Calc 2. All this x has to be the same as that x and the same as those bounds in x. Show of hands if you're okay with that one. If you do this, that's a u sub, that's a, well, half angle, 1/2. 1 plus cosine 2x. If you want to try this on your own, which, man, I highly recommend it, the answer that you get out of this, do you guys see the u sub that you'd have to do, by the way?
There's
Do you guys see the whole, oh man, cosine to the second power, you got 1/2, 1 plus cosine 2x? Try this stuff. Your answer needs to be 4 minus pi over 8, or 1/2 minus pi over 8. But you can all do it, I know that you can. You guys are all smart, I know that you did Calc 1 and 2 and you passed it, you're obviously here, and you seem to understand the stuff. Man, but it is going to have to take some practice. The toughest part, again, is obviously the region. Get the region correctly set up on your double integral, something I really never learned how to do when I was in Calc 3. But that's the biggest idea. Have I taught it to you in such a way that you actually understand what's going on here? So you choose along one variable, one axis first, that's your d whatever, dy or dx. Make sure that your variable here matches your first variable, whatever it's equal to matches your second variable, and you must end with constants. That is the whole idea here. Kind of fun. Was it crazy? Do your brains hurt? Or take a little break here. All right, so here we go. We gotta finish up this section 14.2. We're talking double integrals. The idea is, well, you know the idea. What does a double integral find for you? Volume under a, over a. So we need this finite region to be able to find the volume underneath it, and that's exactly what we're doing. Let's suppose that region is, well, what if I don't give you something that says, hey, x is between two numbers and y is between two functions, or something like that? What if I just say the region is this region on the xy plane that our surface is hanging over? Well, we got to do some things that are a little special. If I ever give you a region where it's not bound by constants, it's not bound by functions automatically, draw that region. Create your own functions, create your own constants. I'm going to show you how to do that. Just keep in mind the idea. We're going to draw a region, this region on the xy plane. This surface is hanging over that region. So we're going to draw that, figure out what region we're over, and find the volume over that region under that continuous surface. So if hands feel okay with the idea behind it. That is really important. I want you to grasp that idea. Can you all grasp that?
Yes.
What is that? Shifted right 1. What's that?
Line.
Y-intercept? Slope? So let's graph it. Let's graph it real quick. You graph it as I graph it. So this guy is a parabola shifted to the right. This thing is a line, y-intercept of 3, slope of -1. Ladies and gentlemen, this is the region that I'm talking about. Can you see the region that's bound by these two curves, yeah or no?
Yes.
So our surface is hanging over here. We're trying to find the volume under our surface bound by that finite region. That's the idea. What I want you to do right now is label these two curves, please. So I want to label this as not just -x plus 3. I want to make sure I know it's y equals -x plus 3 and I want to know that this one is y equals x minus 1 squared. So when I don't give you constants and automatically tell you that our region is between two functions and or between two constants, what I want you to do is draw the picture, get the picture in your head, find the intercepts. Please listen carefully. When you find the intercepts, you're literally finding the constants. You need to find the intercepts. How do you find the intercepts of any two functions like ever? What do you do? So let's do that. Let's set them equal to each other. So if we do, we got this set equal, we're going to find these two intersections. Okay, well, it might be obvious from the graph, but if you didn't have the graph, it's a nicely drawn graph, so you probably could see it. If you didn't have the graph, you'd have to set them equal to each other and find these things.
Isn't it x squared minus 1 or minus x?
Yeah. So on our xy plane, where these two curves intersect on that plane, is that the values of x equals negative 1. Yeah, we kind of see that. And x equals 2. Tell me right now how to find the y coordinates from our x-intercepts really quickly. What would you do?
Plug it in.
So if I plug it in, I'm going to plug in 2. And to either one of these things, I'm going to get 1. So this occurs at the point 2, 1. Plug in negative 1, I'm going to get positive 4. Ladies and gentlemen, that's the second most important part, is just being able to draw your region. I know it's not that hard, but you have to be able to draw it. You have to be able to find the intercepts. Have I given to you enough information so that you can find the intercepts and draw the picture? Show of hands if I have. Okay, the most important part is setting up your double integral. We gotta set this thing up correctly. Now, you always have choice. What's that theorem that says I can do x or y first? What's it called? Fubini's theorem says for general regions, that's a general region, I can do dx dy or dy dx along the x-axis first or along the y-axis first. The most important and the hardest thing to get down is what the correct choice is. This is basic algebra. You can graph, you can find intercepts, that's not bad. The calculus comes in and how we set our double integral up. That can be tricky. You gotta know what axis to go along first. Either the dy along the y or the dx along the x. I'm gonna show you how to do that. It's not super hard once you get the grasp of it, but there's a couple key things that I want you to know. Firstly, the reason why we find our points is because either we're gonna go along the y last, constants between 0 and 4, or along the x last, constants between negative 1 and 2. How we make the choice of what we go along first, that's a different story. That's this. When we look at this thing, by the way, do you have any questions on that, the basic algebra? I'm going to erase it right now. Okay. When we look at this, yeah, I'm going to set up my double integral. I'm still going to have this no matter what. That has nothing to do with our region right now. It's just a continuous function surface over it. So this I'm still going to put. This is what I figure out first. If you can figure out what your dA changes to, dy and dx, then this stuff all plays off of our picture. That's why we draw our picture. So here's how to figure it out. Here's the whole key punchline of this problem. What I want you to do, I want you to imagine going along the x-axis first or the y-axis first and see in which case do you not switch between two different functions. I want to always stay between the same two functions. Now I want to show you what I'm talking about here. If I travel along, don't write this down because I'm going to kind of switch things up a little bit. If I travel along the x-axis first, that would be along the x in this direction from left to right along the x. Head nod if you're okay. Got to go within the region, and I'm going between functions of x. Please listen carefully. If I'm going along the x-axis, even though we graphed this from one picture, along the x-axis, this counts as a different function from that. along the x-axis. Can you do like the vertical line test for the x? That is a different function. Does that make sense? If ever I switch between two different functions, so right here I'm between this function and this function. Does that make sense? If ever I go along my region, still keeping in the x direction, and I start switching functions, if I switch functions, that means two things. Either you need to add an integral and create two different integrals, two different double integrals, or you're going the wrong way. Does that make sense? It's probably you're going the wrong way. So let's see if you can follow what I'm talking about. Right here, do you see that right now I'm between this function and this function according to the x? Yes, no? As I traverse this region, do I start switching a function on one of these sides or the other?
Yes.
Right there. So here between this piece and this piece, that's cool, but then as soon as I go, oh man, that's a different function, that means I need a different double integral. Show of hands, feel okay with that. That's a problem. So, do I want to do dx first? No, I do not want to go along the x direction first because I'd have to create one integral for this piece and then another integral for this piece, because as I traverse the region, I start switching functions right there. That's bad. You do not want to do that if you can avoid it. Now, the question is, can we avoid it? Well, naturally, if we're not going to go dx, we're probably going to go dy, but let's see why. Erase this. If I go dy between functions of y, that means along this path. As I traverse from left to right, I traverse across this, am I always between the same two functions of y? Remember, according to y, this is one function now. X, it wasn't. The vertical line test doesn't work. But here, that's one function, that's one function. So on my region, am I always between the same two functions? Even right here, it doesn't switch because this is one function of y. That's the key. That's what you're looking for. Have as few switches as possible. If you can always be between the same two functions, do that direction first. That's the biggest key I can give you. This is the biggest example that we do in this section, is this one, to illustrate for you the concept of stay between the fewest number of functions that you can. Have I explained that well enough for you? I really want to make sure that you get that concept. Yes or no?
Yes.
Do you understand the concept of if I go this way, x first, I have function, function, function. I basically have three functions. That's negatory. Don't do that, because I'd have one integral from here to here is 1, 2, but then another one, because that's a different function. I start switching functions. This way, I am always between the same two functions. I love that. Let's go dy first. That creates for us always between the same two functions for the entire region. How we draw it, we go, okay, well, what two functions are we going between? Well, what's the bottom function? What's the low function? Is it the x minus 1 squared or the negative x plus 3? What's the bottom one? So I want to first travel between these two functions. I use a solid arrow to represent that. The region is dictated between this function and that function along the y-axis first. Show of hands if you're okay with that one. So dx, heck no. dy, yes. Now let's put it together. I know that you know this. If I have dy first, what variable do I have to have set equal to a function? What has to be right here and right here? What does it have to be? I need y equals and y equals. Head nod that you're with me on that one. Listen, I need you. I need you for 2 hours, 3 hours today. I need you for this stuff. I told you that these are the biggest sections. That's true. 14.2 and 3 are huge, and then 14.6 and 7 are huge, sure. So you need to get the huge stuff down, okay? Do you understand that if I have dy along the y-axis first, I want to be within functions of y. That means y equals functions of y equals something in other variable. That's fine, but I want to have y equals to stuff. Show of hands if you're okay with that one. Whenever you do this, whenever you're going along the y-axis first between functions of y, it has a name. It's called y simple. It means that we're going between two simple functions of y. That's what it means. If we go along x first, that dx first, we're between functions of x, that's called x simple, between two simple functions of x. Does that make sense to you? They just have those special names. I don't even think I wrote it down last time, but that's what those things mean. So here we go, okay, man, you know it, come on, everybody, what's the bottom function of y? Say it out to me, what is it?
Y equals x minus 1.
I want more than what I'm getting from you. What's the top function of the region according to y? What is it?
X plus 3.
So, do you understand a couple things about it? Do you understand, firstly, how to graph the region? Do you understand why we went along the y direction first, the dy, and not the x direction first? Do you understand? So, along the y direction, your arrow should go between, at most, two functions. Two functions. Between one function and another. Put the lower function first, put the upper function up here, it's even in that order, and make sure they're equal to variables according to that. That's the key. Match your variables up. And now that you're with me. What this is equal to should be your last variable. So y first, x second. This variable always matches this. The second variable always matches the second variable. It's literally in the same order. It's kind of nice. So this has to be dx. I use a dotted line to say, well, now I'm going to go along the region from here to here, second. Only be careful about it. You have to go from the furthest left constant to the furthest right constant of that region. But it only has to be according to whatever axis is last. So let's go along the x-axis. Notice we're going along the x-axis, yeah? The x says that also. Hopefully you remember this. Do you remember that these numbers have to be constants for this to work out? You got to end up plugging in numbers. So I want x equals, and I want x equals, but I want them to be numbers. What's the furthest left x constant that we get in our region? What is it? Look what I told you. When you find the points, you find the constants. Do you guys get that? When you find the points, you find the constants. That's why we actually put our points up here. It's -1. But our x-coordinate furthest is -1, and to the right, we get +2. So we need -1 here, +2 there. That creates for us this kind of rectangle that contains our region. X, -1 to x equals +2. Show of hands if you're okay with that one. If we went along the y-axis second, what would our bottom y be? 0. It can trip you up, but the bottom y value is 0 there. Does that make sense? That's why we draw the picture, folks, so that you can actually see these things. Okay, this one, I'm sorry, what was it again? Looking at it?
-1.
2. Beautiful. Let's take a moment, just take 10 seconds, look at the setup. I want you to understand every single thing about the setup. I really want that for you, that you get it, not just follow it, but understand it. Do you understand why we went dy first?
Yes.
Number of functions idea. Do you understand why we have this function and this function where they are? Do you understand why we need to match up this y with that y, and these x's have to come with that x? And do you understand, probably one of the most important things, why we have to end with constants? Do you understand why we have to end with constants? And do you understand where those constants come from? And you get it, you understand everything about it. Now what? Honestly, this is the easy part. As soon as you have the setup done, it's two integrals. We're going to do the inside integral first with respect to y as our variable, fill it in, and then do with respect to x. Why don't you start working on that if you would? I want to see that you guys can actually do this stuff. So try your best to complete this integral. It's not a super hard one. I want at least the first step. I want the first integral, the inside integral done, and I want you to evaluate it. If you want to pause there, that's fine. There's a lot of combining like terms that happen, but I want at least the first step in about 30 seconds. Go for it. Hey, ladies and gentlemen, did I give you enough time to at least do the first inside integral and plug some stuff in? Let's see if you did it, man. Left-siders. If I do this inside integral with respect to just this, right here, if I do that with respect to y, what do we get? 4x cubed dy.
4x cubed y.
Perfect, because x is like a constant, it's like 7, it doesn't change. So this thing should be just 4x cubed y. Show of hands if you got at least the integration part correct. It's like an anti-partial derivative. Now, the reason why we write all this stuff is so that we know what to plug in, and more importantly, we know where to plug it into. So what variable are we plugging in for? Come on, what variable are we plugging in for?
Y.
Which one do we plug in first? The negative x plus 3 or the x minus 1 squared?
Plus 3.
And this is all within some other integral, this other integral, dx. So we've done this integral with respect to y, no problem, it's 4x cubed y. We're going to take whatever our y says, we're going to plug in 4y. That's why we write down what y equals to. That's why this variable has to be x's. Look, that's not what you're doing. I know you're working on it. I want you to pause for just a second, okay? I want you to understand why these things have to be x's and why you have to plug in for whatever variable you just integrated with respect to. If you're integrated with respect to y, you're going to get some y's. If you plug in 4y, it's all going to replace the y's with x's, and that has to match what you integrate next. You should all be left with just one variable. That's what's happening here. If you do that, we have this 4x cubed, and then a negative x plus 3, minus, and you can do this too, if you want to just keep that 4x cubed out front. That can act like a constant. Just keep that 4x cubed out there. Do this minus that. If you want the 4x cubed in both places, you can see you're going to get the same thing. It doesn't really matter. Me personally, I like this better. That makes my distribution combined like terms a little bit nicer, but you can do whatever you please. What I would like to know is if you made it at least that far, or maybe you have this distributed. Show of hands if you did. Listen, I'm not super interested in your ability to distribute and combine like terms. I know you can do it. I know that's great. I'm going to skip that. I'm going to just show you what it is after you've distributed and combined like terms. My main points here are these. Can you draw the picture? Can you set it up? That's the key. Can you do the first step? Because I know if you guys can do the first step and plug it in, the rest of this is kind of child's play for you guys. You guys are smart. You know how to do Calc 1. You know how to do some integrals and Calc 2. That's great. But I don't, you do. That's why you're here. That's fantastic. It should be encouraging that after we do the setup, this stuff is knowable. You know it. You with me? Knowable is a bad word. You are able to know it. You do know it. Let's just prove it to me now. So when we distribute and combine like terms, some of y'all are checking your algebra right now, huh? I get that. You guys get the same thing?
Yeah.
It's fantastic. That's really good. Hey, tell me something. Is this a super hard integral to do for you? No, that's a piece of cake. That's Calc 1. That's awesome. Notice, we plugged in all the x's so that we would match up with our x's. We had our x constants last. That way, when we evaluate our x's, we're plugging in the correct numbers. You don't want to put y constants if you're integrating with respect to x last. You have to match that up. So we go along one axis first between functions, and then another axis second between constants. And you want to match up the correct constants to the correct axis, and nothing could go wrong. That's a lie. Lots could go wrong. But you can do it. You know how to set it up. That's the most important part. If you've all done this, simplify it. Well, I don't even know if I want to give you the integration. Here it is. That's what I got, and then we're evaluating. Of course, these are x constants. That's fantastic. That means we plug in -1 and 2. I've done it. I got 72 over 5. If you want to check your work later, 72 over 5. I'm not super worried about you plugging in numbers at this point. What I am super worried about is you setting up and getting at least this far. I know you can do the rest. Show of hands if you feel okay with at least getting this far. Hey, that's 10 points on a test right there. That's a good test question. Do you take notes on that when I say that's a good test question? Go, hey, by the way, that might be on your test. Like, that's not gonna be on your test. He's just lying. Fuck crap. That's gonna be on your test. Okay. Make sure you know how to set up a double integral from a region like that. That is what I want you to. This is the level to which I want you to understand. Okay. Something very much like that. Now, any comments, questions, or anything before we continue? If that's not fun, I don't know what's fun. That's funner than Disneyland. There's no lines to do math. Trust me. That's why you're getting math degrees, because there ain't nobody in front of you. All right, you're going to be the first one to the party. Woo! Job security. I mean, it's great fun. It is fun. It's fun to do this stuff, but there's no one waiting for you to do this. You jump on this stuff and get it done. So, comments, questions before we get going on the next stuff. Now we're going to talk about some weird. Because it's kind of weird, right? What did we do? What did we just find? Honestly, what is it?
Volume.
The volume. It's a volume. Under that surface, we don't know what it looks like. Probably can figure it out. Cylinder along the y-axis, but whatever. We just found the volume under that thing over that really weird shaped region. That's pretty darn cool. This shoots up in space. That goes over it. We found the volume of that. Crazy. That's what we're doing. Now for some slightly weirder stuff. Sometimes our regions get a little funky. We're going to talk about one weird region like this. I want to show you that whenever you're given a region that you're given some points, the path between 2 points is going to create a line for you. Here's what you need to do. Number one thing, as you should be doing right now, draw out that region, plot the points, and create some lines between them. Once you do that, hey, if you gleaned anything from this example, hopefully you gleaned this. You need 2 functions to go between. Do you get me? You have to have 2 functions to go between. So we need to at least get some functions for these 3, count them, 3 lines that we have. One of them is really easy. One of them, this one is y equals 0. How do you find the other ones? Well, I kind of give you some notes here. Tell me, if I give you 2 points, can you find the equation of a line between any 2 points? You just have to, this one, not bad, horizontal y equals 0. This one has a slope of 1. You have an intercept at the origin. So this is what? Y equals x or x equals y. It depends on which direction we want to go first. So right now I know this is y equals x. Yeah, that's good. Or x equals y. Listen, it matters. It matters what order you have them in because it matters whether you want to go along the x first or the y first. Are you with me?
Yes.
Seriously?
Yeah.
Okay. This one, if you want to figure that one out, you got to find the slope of that. That's slope of -2, and it's a y-intercept of 12. So we get to choose between y equals -2x plus 12, or if you solve for x, -6 plus 6 plus 6. Ladies and gentlemen, listen, I'm not going to go through finding the equation lines. What I do want to talk about is, do you understand the necessity for us to have two versions right now? Since we don't know whether we're going X or Y first. I want to have both cases ready for myself. I want to have Y equals, I want X equals. Y equals, and I want to have X equals. So I guys feel okay with that one. Now it's up to you. I want you to think. Just look at the region for a second. Here's our region. Do not say it out loud, but I want you all thinking about it right now. You tell me in your mind, just think it to me. Tell me in your mind, what's the appropriate first direction? Just think. Don't say anything right now. What's the appropriate first direction? Along the X first or along the Y first? Keep in mind what we want. We want to not switch functions. We want to not switch functions across the entire region. Think about it for a couple seconds. Is there a way that you can go traverse this region across one direction and not switch functions? Is it this way? Is that a good way? Because right here you go, oh, between two functions. What functions? Well, y equals x and y equals 0. That's between two functions. But as soon as I do this, notice, here's y equals x, y equals x, y equals x, y equals, this one's all y equals 0. Y equals x, y equals x, y equals negative 2x. Oh, that is switching functions. That's what I mean. I want to be within the same two functions for the entire region along that axis. Is that clear for you? That's what we're talking about. It's a little clearer to see here than it is here. This one in the y direction, right at this point, switches functions. It jumps between two different functions. So fans understand the concept. Let's check the x direction. In the x direction, oh, that's kind of nice because that doesn't create a different function for that x. It's just, it's our y equals 0, kind of that horizontal line. Am I always between the same two functions if I go along the x direction? I want to always say it's x equals this on the top, right, and x equals this on the bottom, left. I want to always be between the same. Well, I'm always between x equals y and x equals negative 1/2 plus 6 for the entire region. That is the way to appropriately set up a double integral. Try it. Try it. I want to see this now. That's going to be some function of x, y. I don't know what it is. We're not talking about that right now. It's all about the setup. I want you to set that up. So set up what goes first, the dx or the dy, and set up these two functions. Go for it. Have you already done it? Try something. Don't wait for me. Don't wait for me. Come on. You can do better than just waiting for me. You got to try it yourself. Even if you make mistakes, it's okay. Ladies and gentlemen, the first thing I want you to do, of course, is draw your region, find out the points, find out the equations, find out the functions, and figure out which axis you go along first. We've already determined that. Which axis do we go along first? The y-axis or the x-axis? So draw a little arrow. We're going from here to here for the entirety of this region along the x-axis. That's what we're doing. We're going along that. Okay. So what comes first? The dx or the dy? dx, because we went along the x, that increment goes along the x-axis first. And we're going between, okay, hey, here's your big test here. What should be here, y equals or x equals? This has to match up with the variable you solved for, the variable that is equal to your function. This is kind of tricky. What's the bottom one? What's the bottom of our region? Remember, we always go from left to right or down to up. What are we hitting first in our region? What are we hitting? We're not using that one because I'm going between functions of x. That's why we had the dx. That's why we had the x equals. And where's our region ending? At what function of x?
Negative 2x.
Beautiful. Excellent job. What's the last thing I'm going to do? Where am I going across next? So I've already gone along the x-axis. Now I'm going to go along the y-axis. That means I need a dy to wrap this up. That means this variable has to be y's, and it's got to be constants, but they got to be y constants. Now, where do we go? You have two choices, it's either 0 to 6 or it's 0 to 4. What's the appropriate choice? That's why we draw this region, that's why we draw our arrows. So along the y-axis, I'm hitting a y value of 0, and at the very end of our region, I'm hitting a y value of 4. That means I go from 0 to 4. It's all about the setup, but I want to make really clear. I want to make it clear to you how to set it up. Have I done that? Do you understand how to set up these regions right now? It depends if you do. Cool. Is it making sense?
Yes.
Are you enjoying it just a little bit?
Yeah, sure.
You can lie to me. Are you enjoying it just a little bit? Yeah. No. Well, you're supposed to say no. No, I hate it. That means you really... Whatever. All right. Now, can I finish off the problem? Do you have anything that you can integrate? It's all about the setup. All this, that's proving to you something. That this region has nothing to do with the function. It's all about figuring out what you're going across, setting up your region. Here's the hardest part. It's something I never learned well until I actually started teaching this stuff. You go, oh, that's how it works? Yes, I'm trying to pass it on to you. This is how this stuff works. The function itself, it's just flying over this. It needs to be a continuous function over this defined region. And that's what you're doing. You're taking this up, creating this kind of triple plane. It's coming up, it's intersecting some surface, and you are creating teeny little rectangles on that piece, finding the volume over each one of them, adding them up. We talked about that in 14.1, but this is what we're doing every single time with double integrals. Now, we got maybe one more kind of problem, and then we get some really cool stuff. I'm going to teach you how to fix double integrals, because sometimes people jack them up, right? Have you practiced double integrals? Okay, well, start practicing them. You'll see what. You're going to be happy. You're going to be happier than a red pen on a stack of Calc 3 tests. I mean, what? I'm sorry. Too soon? I'm just kidding. You did great on your last test. That was really good. If you haven't collected that, make sure you get it from me before you leave. I want to make sure you get something for this weekend to look over, okay? So, we can also be given double integrals in a slightly different fashion. I can word it a little different. So I'm going to do that just to give you some practice on how you might see it, like say for a test, or like on your homework or something. So let's find the volume. Might give up. Just done. Because it looks hard. It looks like, what is all that stuff going on? Look, if you were to graph all this, which I don't want you to do, all I want you to graph is the region. We're going to talk about how to get that in a second. If you were to graph all of this, you know what? Maybe you can. Maybe you can picture it. If you were to graph that, how many variables do you see? 2 variables in 3D creates a what? Cylinder. It's a cylinder along what axis? Very good. Cylinder along the x. What's the picture of it? Circles. That's a literal cylinder along the x-axis. Can you picture it? Z equals 0 is the xy plane. That's all that is. That's saying that this is the cylinder cut by the xy plane, but then also cut by the y equals 0. Y equals 0 is also a plane. That's that one going this way. This way, the xz plane. That's what that one's doing. So I have the cylinder. It's cut in half. It's cut in a quarter. That's what that does. This one says x equals 0. Well, that's the x equals 0. Let's see. That's x equals 0. That's the yz plane. So I have a cylinder. It's cut in half. It's cut in a quarter, and it's cut lengthways. So I have this little kind of a quartered hot dog in the positive first octant. And then I have that. True or false? That's also a plane.
Yes.
How many variables? 2. That means it's a cylinder, but it's not, it's a line cylinder. That means it's a plane. And I have this plane cutting across that first quadrant, cutting even more of that. So we're talking about this 3-dimensional cylinder that's cut up by a series of planes. Here's how to cope with this. Notice how all of these are planes, and they can be projected onto the XY plane. Do you see it? This is the XY plane. This can be graphed on the XY plane, this can be graphed on the XY plane, and that can be graphed on the XY plane. This creates for you your region. Anything with a Z in it is going to create your surface. Keep in mind, surfaces can always be found by setting a function of 2 independent variables equal to Z. Does that make sense? So our idea here is if you're not given a surface that's automatically defined as Z, it's implicitly defined, solve it for Z. Then use all the other stuff and draw your region. So here's what I want you to do right now. What I'd like you to do right now is focus on this. These are all planes, but they all have a projection on the XY plane. Can you please draw that projection? I want you to draw the region. Try it now. Hey, can you draw Z equals 0? Right here. That is it. It's XY plane. Can you do Y equals 0? Yeah, that's what type of line? Come on. What is that?
Right, so it's a horizontal line. So, right is there?
Yeah,
That's horizontal.
just that one. Just the x-axis. And then this would be the y-axis. And then this, you go, well, you know what? I learned how to graph some equations of lines. Notice it's a plane, but on the xy plane, it's going to be a line. Cover-up method, pretty nice. Just cover up y, you get x-intercept of 1. Cover up x, you get y-intercept of 2. There's your line. Can you see the region that's created by these planes? It's this nice little triangular region. What I want you to do is write out the equations of all of these lines that create your region in, well, unless you really know what you're going to do with your surface, in both variables. So for me personally, I would do this. I'd say this is either going to be y equals negative 2x plus 2, or it's going to be x equals negative 1/2 y plus 1. I've done that right. I didn't do that right. Did I do that right? Crap, I don't know. Yeah. Yeah. Okay, good. Making sure. This one's already nice. It's already solved for x. This one's already nice. This one's already solved for y. But I want to have the ability to go between any two functions that I want in any direction that I want. Show of hands, feel okay with that one. Now, the next thing I want you to do, after you draw your region, after you have all of your equations set, I want you to solve for z on that surface. Try to solve for z on that surface, please. How would you do it? First step. What's your first step? I need more from you. What's your first step in solving from z? Subtract what?
Y squared.
Okay. After you subtract y squared, what's your next step in solving for z? Now, when you take a square root, and it's not on the paper, you take it, you need a plus and minus typically, correct?
Yes.
Since this is bound by z equals 0, it says we're above that, we don't need the negative, we just need the positive part of that square root. That's what the z equals 0 is there for. So okay, so z squared equals 9 minus y squared. Square root of both sides. Disregarding the negative because we are above this. We're bound by these pieces and the top of that surface. We have that. Hey, now that you're with me, we got to move a little quick on it, but I want to make sure you understand at least the region. Do you understand the region? Now it's time to set up our double integral. So draw yourself a double integral. Put your function. Hey, look, functions are equal to z. This is a function equal to z. This is how you, step by step, this is how you set them up. You draw your region, you figure out your function. Most of the time it's just given to you, but if you have to solve it, just solve it for z. Put your function down, and then do the most important part. Set up your x direction first or your y direction first. Now let's look at the region here. Let's see if you really got anything out of it. Either way I go, am I always between two functions? Good, you're catching on. I'm not switching either way. If I go this way, it's always this function and this function. I'm always between those two. If I go this way, it's always this function and this function. That's why we write out both versions, so you have the option of doing this. Now, what is the better option? This is the part where you look at your integral. If the region's not telling you, man, a lot of times, the region just dictates what you do. It says, you got to go this way, otherwise you're switching functions, you have multiple integrals. That sucks, man, don't do it. But if the region's not telling you, like, either way I go, I'm good, let the integral tell you. So let's look at our integral. And try. Just put down dy first and see what happens. Put down dx first and see which one's easier. Let's put down dy, but I hope you're paying attention. Let's put dy first. Don't put it down. Just think for a second, okay? Don't put it down. I want you to think through it. I'm trying to get you to think about this stuff. Put dy first. Could you do this integral with respect to y? Could you do it?
Yes.
What would it involve?
Trig sum.
Trig sub. Do you want to do a trig sub?
No.
If I, yeah, I'm a sadistic guy. What's the one where you do it to yourself? Oh, I'm a masochist. Don't be that type of person. Okay, that's messed up, dude. If I did this, could I eliminate a trig sub? Yes. Well, at least for the first part. Yeah. At least get one easy one out of this. Let's go dx first. We're actually not going to totally eliminate the trig sub. It'll just happen last. But that's kind of nice. And here's why it's nicer. Because if you do the trig sub first, you have to plug functions into something that has trig sub stuff in it. All right, that means a lot of sine and sine inverse, or cosine inverse, all that secant inverse, all that stuff. I don't want to plug into that because that's horrifying. Okay, don't do that. So at least get one easy integral. Do you understand that if I did dx first, that's all a constant, and I just get an x in front? Let's do that one. So right now, first, did you understand the concept of doing the x first? That way I make my integral easy. So the region doesn't care, but the integral might. dy, trig sub right off the bat? No. dx, at least I get an easy integral? Yes. Do I need to go slower on that one, or are you guys okay with that? Okay. Can you please, right now, set up what this, and knowing that we're going across dx, knowing that we're going dx direction first, set up this and this. I'll tell you what, it's going to help if you go to your picture and you go along the axis that we're traversing first. Are we going y direction? X direction. Draw that first. And then that will tell you between what two functions you must write your integral. I'm only going to give you about 10 seconds, but I want you writing something. Do you know the reason why I have you write this variable here and this variable here? Do you know that reason? It's so that it helps you, so that when you look at your graph, your region, you go, okay, I need stuff where x is equal to other things. That's if I have dx, I need x equals to other things here. Well, your picture's going to tell you. Right now, I have to go between x equals 0. That's where I'm starting across this region, and I'm ending at. That's so you don't pick this. So you go, oh, I'm going to put it. If you don't have that, you know what? I used to do a lot. I put, negative 2x plus 2. Because that's obviously the function, that's how I drew it. But is that going to match up very well? See what would happen here if I used that, and I did my integral, I'd plug this into, I'd probably choose y anyway because I'm making mistakes on it no matter what. And then I'd have a dy. And I'd look back and go, wait a minute, I just plug in x's and I have a dy. Is that going to work out very well for me? That's a big problem. That's why I have you write out this variable and draw the picture. Because if I'm going along the x-axis, it has to be between two x functions. That's why I put x equals and x equals. Yeah, x equals 0, that's great. Then I'm going to hit this line, but I'm going to choose the one where it's solved for the variable of the axis that I'm traversing right now. It's not y, it's x. X equals negative 1/2 y plus 1. Truly, I need to know if you understand it. Show of hands if you do. What's the next thing I'd write? Let's see if it flows. I have x first, x equals. I have y second, and I have some values I can plug in for y. That's what I want. I want these variables to match up with that variable. I want this variable to match up with what is equal over here on the left-hand side. Good to go? Can you tell me the numbers?
0, 2, 2.
They got to be y values. They got to go from the smallest y value on the region to the highest. 0 to what?
2, 2.
Yep, because y value of 0 all the way to y value of 2. That's perfect. That's the hardest part. Can you please do the first step? Make sure you get that right. Do the first step. If you haven't done it already, do it now. I gotta be honest with you, I'm not spending a whole lot, even though this is a long, kind of hard integral, we're not gonna spend a whole lot of time on it. We're gonna do the first step. I'm gonna show you what to plug in, and we'll talk about how you'd evaluate it. If I'm integrating with respect to x, everything besides x's are held constant. That means this is one big number. And I just get an x right in front of it. Okay, come on. Come on, what variable am I plugging into for this? What variable? X. That's why I write it down. If I plug in x equals 0, this whole thing is gone because I'm having 0 times something, that's cool. If I plug in x equals this, what we end up getting is this integral, all in terms of y, which is exactly what I want. Y equals 0 to y equals 2. I've got this, negative 1/2 y plus 1. It must be in parentheses because I'm multiplying it by something else, some function of y, dy. These are in y's. These are all y's, and that's a y, and that's what we're looking for. We just changed something into Calc 2. That's what we're looking for. Changing Calc 3 into Calc 2, or even Calc 1. Head nod if you're okay with that so far. Now, how would you go about solving it? You want to try stuff like U subs, but it's not going to work. This has to happen this way. I want you to do it on your own. We don't have time for me to go through the whole thing. Okay, it's take about 15 minutes for me to fully explain. Not hard, you've done it, but this would be distribute this. Distribute that. Maybe pull that negative 1/2 out. You do whatever you want on that, I really don't care. How would you do this integral? How would you do that? Easier. Easier than by parts. Easiest thing you know. Will the U sub work? Do you remember U subs?
Yeah.
I just taught them in my Calc 1 class today. So I'm like on the money with U subs. Like, yeah, U sub. I see U sub everywhere. It's fantastic. Best thing ever invented.
Oh, yeah.
Besides ice cream. Ice cream is pretty darn good. And cars. I love cars.
USub was discovered.
Ice cream was discovered. It was there from the heavens. No. Don't know what I'm talking about. Anyway, that's U sub, because the derivative of this piece is negative 2y. I don't care about the negative 2. The y is going to be gone. That's a u sub with a u to the 1/2 power. Does that make sense to you? That's u sub. This you are not escaping the trig sub. That's trig sub. So you would do a u sub. You probably change bounds. You do a trig sub. How you do a trig sub? I honestly don't care. You could literally do a trig sub with the triangle. You could use a table. You could use a calculator. At this point, my main goal is getting you that far. That's my goal. How you do your integrals after that, I don't care, man. Tables, just memorizing them, calculator, whatever. Do you guys understand the concept? We're past that. This was taught to you before. You know it. I know you know it. Trig sub, whatever you have. Here's the answers that we should be getting out of this if you want. By doing u sub and changing bounds, you end up getting negative 1/4 times 2/3 u to the 3/2. And changing bounds will give you u equals 5 to 9. You can even do that here, actually. It'd be easier. This guy gives you 9/2, a sine inverse of y over 3 plus y over 2, and you get the u back in this, or the theta if you use theta, 0 to 2. If you want the final answer, here's the final answer. It looks nasty. It looks so nasty. But here's the point. Is this, if you put it on a calculator, is this an actual number?
Yes.
What does that number, oh man, what does that number represent?
Volume.
The volume of that weird shape that we just created in our mind. That's what you're finding here. The volume bound by this series of planes and surfaces. It's pretty incredible. My encouragement to you, try this on your own to practice your integrals. This is outside of our class. Okay, I've taught most of you your integrals, but this practice is good for you. You need to still be able to do it. We're just not going to cover it in class. Yes.
On a test, would we be likely to see one where we have to solve them completely like this, or would we just have to set it up?
You are very likely to have stuff like this to get down to this part. Sometimes, if I'm feeling friendly, I might just say set up the integral. Is that likely?
No.
Sometimes, if I'm feeling friendly. Am I a friendly person at heart? You want me to be. I do bring you candy. That's just because I'm bribing you. Yes, I'm friendly sometimes. It depends. It really just depends. I would tell you you better darn well be ready enough to draw the picture, set up the double integral, and complete it all the way down. You better be ready for that. That's the level I need you at. Because you know it from here. I'm getting you this far. And then you know the rest. That's the point. Show fans you feel okay with the concepts of them. Okay, so well, you know, last thing is, you'll see. Oh, you will see. I'm gonna give you an easy one. I'm gonna give it to you all set up nice and everything. Yeah. 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 Try. Go. All set up and everything. Set up for you. You're done, right? Are you? Well, yeah, of course you got to write down first. Did you write down first? Hey, you're scribbling furiously. I'm wondering why. Here's why I'm wondering why. If you try to do this integral with respect to x, what's the integral of e to the negative x squared with respect to x? Well, is it a u sub? It's not multiplied by anything. It's not a by parts. It's not a trig sub. It's not a simple exponential. This is done with series, actually, a Maclaurin series or a Taylor series. Let's go ahead and let's bust out the Taylor series on some double integrals. That sounds like a good idea. Yeah, because those end, right? Do you want to do that? You want to do that?
Sure.
Here's what happened. Oh man, you got to be paying attention to this example. This is a good one. Someone screwed up their integral. Someone screwed up their double integral. Because someone said, hey, yeah, my region looks great. We always go along the x-axis. And they didn't pay attention to that example that we just did. How the region might tell you either way is good, but the integral tells you one way is bad. Because right here, can you do that integral? You can't without Maclaurin or Taylor. You can't do it. This is not possible with respect to x. Does that make sense? Now, what's Fubini's theorem say? What's it say? All I heard was argument. When I hear that, I think, I hate you, Leonard. This is what I'm saying. I hate you. That's all I hear. What's Fubini's theorem say? What's it say? Either one. But wait. You don't write yet. Watch before you write. Would this make it easier? Can you do the integral of this with respect to y?
Yeah.
Absolutely. That's super easy. You get y e to the negative x squared. You guys see it? It's a partial, like an opposite partial derivative. And opposite partial derivative is easy with this. But here's the problem. I need you to see the problem. If you have this, the third and last reason that I have you draw x equals and y equals is because this right here would be x equals and x equals. Does that make sense? This right here would be y equals and y equals. Does that make sense to you? If I just switch these things have to change. Does that make sense? Someone messed up their double integral and you're about to fix it. You could title this Fixing Double Integrals if you want to. We're going to make this possible because someone screwed it up. Here's what we do. We use that idea of me telling you, hey, that's x equals 2y and x equals 2 and all this stuff. Could you recreate the region that someone had to draw that? Yeah. Let's write down everything we know. We know that our region goes from y equals 0 to y equals 1. We know our region goes from x equals 2y to x equals 2. Please notice something. Please stop what you're doing. Stop writing, stop doing anything. Just look. These are in order. What this says is we go along the x-axis. We hit this one first and we hit this one second. It has to be in that order. Does that make sense? You don't get to make up your own math here. You don't get to just go, I'm going to go from here to here. Because why? I want to. You don't get to do it. You have to follow this setup. So let's try it. And then our whole goal is if we can draw the region, then I can redefine my functions and I can redefine the double integral. Does that make sense? So let's backtrack, do like a 10-second recap. Do you see the problem with how it's set up right now? Well, the problem is it's freaking impossible, so that's the problem. The solution is we got to switch these. But what that means is that instead of going along the x first, I need to go along the, yeah. So I need to know what the functions look like. Let's go ahead and try to draw a region. Hey, can you put all of these graphs on that graph? All of these lines on that graph. Let's do it. Y equals 0 is there. Y equals 1. Well, that's like y equals 1/2 x if you want. We can solve it right here. and we have x equals 2. Well, that's pretty convenient. Y equals 0, y equals 1, well, yes. X equals 2, and oops, y equals 1/2 x. Right, now it's a small 1/2. Sorry, I'll make that bigger. Y equals 1/2 x. I want to show of hands if you can draw those pictures and feel okay with what we got. Show of hands if you do. Listen, this is why your understanding of what you're between is actually important. You see, a lot of people don't quite grasp this, and when they go, hey, show me the region, they do things like this. Look, stop. You need to be focusing here. I know you're working on it. Don't work on it right now. Focus on the setup so I know that you know it. Okay, you know? So, a lot of people may get confused and talk about that as my region. That's why this stuff is important. This setup says, here's your region. You started going along the direction of what axis first? What did this guy do? Along what axis?
Yes.
The x-axis. They hit this function first. Remember, this came from x equals 2y. It's the same. Or they said, I'm going this way. I hit this. Oh, I didn't hit this. I didn't hit x equals 0, did I? There's no x equals 0 up there. It said, I hit this function first. I traversed a region until I hit x equals 2. That is what gives you the region. Because it can be confusing. If you just draw all the lines, it ain't going to tell you. You have to draw the lines and then look at what they mean. This said, along the x-axis, I hit this function, and then I cross the region, and I finally hit that function. I hit this function, x equals 2y. I cross the region, and I finally hit x equals 2. That's the way that we set this up. Does that make sense? And then the going from 0 to 1 makes sense, but it's only within that region. This has nothing to do with it at all. It's just giving you the constant. Head nod if you're okay with that one. Do you see how key that is? To fix someone's problem, you have to understand the problem. We're fixing this guy's problem. Now, okay. So if this was the wrong way, we know why. I want to do this. I want to change this into a different double integral. I can't change this, but I can switch these. Now let's make our picture better. Let's go between two different functions. What this says is along the x-axis was the bad choice. We've talked 10 minutes about why that's the bad choice. What axis do I want to traverse? Along the y first, across that region. So it's the same region. You can't change a region. But instead of going this way, I'm using a purple pen. You can use a different color if you want to. Some people have seen this is a good idea. Put a squiggly line. I know it's bad notation. I'm sorry. We just don't have a better way to do it without drawing a separate region. If this is your first, I've drawn it squiggly before. Say, hey, this is what the person did. It's wrong. That's why it's squiggly. It's not good. And then we go, now let's make it better. Let's go the opposite direction. I want to go that way first. Does that make sense to you? I want to go that way first. If along the x was wrong, let's go along the y. Now you fill it out. If I go through this region, what's it start with? I have to have what variable equals something here. Come on, help me out. What variables equal something? So y and y. If I'm along the y, it's between two y simple functions, y equals and y equals. This is a y simple, x simple did not work. So y equals, hey, where's it start? What y function does it start at? 0. That's why we label it. It's got to be y equals something, that's 0. What y function does it end at? Beautiful. That's why we label it. Y equals to y equals. If you're going dy first, you better be between two y equals functions. That's it. That's the whole shebang. The rest of it should be pretty easy. Now I need constants to match up with my x. What's my x? 0 to what? 2. Yeah. My x constant is 0. My x constant is 2, and that takes me across the whole region. That's the plan. Do you feel okay with the setup? Now, could you do it? Try it. Try the first integral. See what happens. It's going to be nice. Going to have fun. How can you not? It's Calc 3. My goodness. This is the Disneyland of mathematics. So many rides. So cool. As you're doing that, I'm going to put up another example. We're going to seriously focus just on the setup because I want you to go through this one more time. Then we're going to be done with this section. Did you do the integral with respect to y and get y e to the negative 2x, and then inside of the integral with respect to x after that? Matches up perfectly. We're going to plug in for y, we're going to replace it with x's. It's going to match up with our second variable. That's fantastic. Y equals 0. That's going to give me 0. No problem. We get an integral from 0 to 2. We get this 1/2 x e to the negative x squared dx. Did you make it that far? Tell me, everyone in class right now, what solves that integral? What does it? Subs. Fantastic. What's the u?
Negative x squared.
I see it. I see that right here. That's fantastic. We can even change some bounds. Just please be careful with this. If you're going to change bounds, you don't get to put these out of order. That's not something you get to do. So when we do all of this, we have a 1/2, we have a negative 1/2, that's negative 1/4. We still have our integral, but this 2 was mapped to a u of negative 4. This 0 was mapped to a 0. This whole piece, that's x dx, you get the x dx is gone, you get a du. We already took that negative 2 multiplied by the 1/2, we got negative 1/4, and we have e to the u du. We've done some advanced substitution, nothing is really beyond you guys. I just want to make sure, and this is a different technique that I typically teach in Calc 1 or 2. I'm doing the fast way, the way you don't cross stuff out way. Either way you want, I don't care how you do your subs. I want to make sure you guys get down to that far, so if you can. Now, the reason why you don't get to just randomly pick where these two guys go, you go, wait a minute, negative's got to go down there. Well, you're right. But I can always switch these. If I switch the bounds, it changes the sign of the integral, though. So I could change this to positive 1/4 integral from negative 4 to 0. E to the u du. I can do stuff like that. You guys okay with that one? Properties of integrals. Hey, in the hardest problem ever, what's the integral of e to the u? Love that one, man. That's the best. So 1/4 e to the u. We plug in 0 first. It does not go to 0, it goes to 1. We plug in negative 4 second. Your answer, this is perfectly fine. 1/4, 1 minus e to the negative 4. That's it. Plug in 0, get 1. Plug in negative 4, you get e to the negative 4. Is it a number? That's a volume. That's what this represents. Are you with me? Kind of fun? A little bit? Are you? If it's not fun, that's fine. As long as you know how to do it. Do you understand the setup? Are you starting to understand it more? Okay, here's what I want from you. This is going to take a little bit of time. What's going to happen is I'm gonna talk about this for just a while. I'm going to pause the video. I'm going to give you a few minutes to do it. We're going to take our break. When we come back, we're going to go very fast through it. Okay, so this is something you need to try right now. Well, you know what? Maybe we won't. I won't pause it because I want to keep this continuous. Maybe I'll walk you through it about every 10 seconds. I like that anyway. So here's the way to look at it. Firstly, double integral. Someone set it up. We're going to try to do the integral the way it's set up. And you okay? Yeah, I love sine. That's fantastic. But it's not sine to the third. It's sine of y to the third. This is in here. Can you do the integral of sine of y to the third dy? Can you do it? Not a u sub. It's not multiplication, so it's not by parts. It's not a trig sub. Do you know anything that takes care of that? No. Nothing nice. So, would this make it better? Look at the board. If I switched this, would it make at least the first integral possible? Yes, that's our idea right now. You tell me right now, the way this person has set it up, what variable has to go right here equal to this thing? What variable? Come on.
Y.
Good. And here? Across which axis are they traversing? What direction are they going in first? Along the y or along the x? We want to switch that. So what I want you to do is write down all of these functions, and I want you to graph them. So try writing them down first. X equals 0 to x equals 4. Write them down in order. Y equals, what's the first one? What's the first y function we should come across? Y equals 2 or y equals square root of x? That's first, and then we're going to hit y equals 2. Put at least these three up there, please. You should have at least that on the board right now. Yes, no? Now, this one, y equals square root of x. Well, you plug in 0, you get 0. You plug in 4, you get 2. So it's this square root function that does that. Now, I'll tell you what. A lot of people are going to screw up this. Not you guys. You guys are going to know what you're doing. But a lot of people who really are maybe not here, just don't pay attention, different calc classes or whatever, they're going to screw this region up. It's very, very easy to do. I want you to see why it's so easy to do. Right now, do you see the two different regions that could be created here? This is why your understanding of how the regions work with your double integrals is so darn important. Because this will tell you, it'll tell you what you're doing. It says, I'm going along the y-axis first. So let's put our pencil down here, or our finger down here. We're going to travel this way first. What this says is, you don't start hitting your region until you hit this function first. Then you traverse your region until you hit that function. Does that make sense? Does that make sense? You sure? Does that region start immediately right here? No. It says, no. The place that we start our region has to be along this axis, going this way, when we hit that one. So we go, well, okay, we start right... Oh, we don't start until we get to there. And then we end when we hit y equals 2. I'm going to make it curvy to say this is the first, this is what was originally given to us. But that right there tells you what region you're talking about. It ain't this one. All that x does is give us that constant. That's all it's doing. Ladies and gentlemen, I truly need to know if you guys understand why it's this region and not that region. Do you guys see it? It's all given to you by our first axis. It says you're along the y, but you have to be between these two functions. That's what this says, and that's what that says. Now let's switch it. If this isn't right, then what I want is a double integral, same function, but I need to have it dx. If dy doesn't work, then dx has to work, or we can't really do it. Okay, this says I want to go along through the same region, man. Same stuff, but I want to go along the x-axis first. So to traverse this whole region, well, I need to start here. I need to end when I hit this function. Let's solve that for x so that I can be between two x equals functions. How would I do it?
Square,
Yes.
whatever it says.
So if I'm along the x, I need to be between x equals and x equals. Here, I'm between x equals 0. Hey, that's an x function. That's right there. That's fantastic. X equals 0 and x equals that one, y squared. Let's see if it makes sense to you. Can you see where the 0 is coming from, where the y squared is coming from? I've got along my axis, I have x equals functions. I get the variable I'm equal to, second. That's what I want, so that when I plug in, it matches up. Now, how about the y constants? Right-siders, you guys, tell me what the y constants are. Where's the y start for our region? I wrote it down to ruin the suspense. To what?
Two.
I'm not going to do it for you. I'm going to give you the answer. I want you to do it for you. I'm going to talk you through it a little bit. So here you go. Could you now do this integral with respect to x? What's it going to be? What would you plug in, and where would you plug it in?
X squared to 2x.
So this would go here. X equals 0 would be gone. So I'd have x equals 0. That doesn't even matter. X equals y squared. So we'd have y squared sine of y cubed. Don't leave me hanging. Yeah, u sub. Just do u sub. Do a u sub, change the bounds. It's all in terms of y. It's going to work out just fine. The answer is 1 minus cosine 8, weird answer, over 3. See if you can get it. See if you can get it on your own. That's the end of our section. Are there any questions before we continue? Any questions at all? Have I made the regions make sense to you? That's the most important part. It never made sense to me until I started teaching this stuff and go, oh, that's what's going on. Hopefully you know right now, because you're supposed to, what's going on with our regions. That's the hardest part, is setting these things up. Everything else, guys, you know integrals. And that's encouraging. So as soon as you get the setup down, the rest of it gets a lot easier. That's the idea.